So do the others have exams or something? Any idea? That's okay. Hi, Shiv, can you hear me?
Yes, sir.
Did you guys get the homework that was to be done? You guys as well. Anshul, Path? Acha. Okay. Shiv, you have doubts on the homework?
So actually, I'm not finished yet.
Okay, fine, cool. ठीक है. No, not yet. So in the last class we had a look at this concept called as instantaneous axis of rotation. We revised work energy theorem, so that would involve kinetic energy for all bodies in general, so rolling, translating at the same time. Okay, and we also had a look at angular momentum. So if you missed last week's lecture, I'll just give you a quick recap. So this is basically just a quick recap. Angular momentum in fact आज यही देखने वाला है, कंजर्वेशन ऑफ एंगुलर मोमेंटम देखने वाला है, तो थोड़ा इसका एक क्विक रिकैप बस दे रहा हूँ. The formula that you're going to use is ICM omega plus RCM cross M VCM. ICM omega plus RCM cross M VCM. Yeah, cool. So how does this work? So for instance, imagine ki I have some, let's say I have a sphere, okay? And let's say that sphere is having a mass of 2 kg, okay? And let's say that sphere is having a radius of 3 meters, okay? And let's say this is a hollow sphere, okay? And let's say the sphere is just going, its center of mass is going in that direction with a velocity of, let's say, 2 meters per second, okay? So that's your center of mass velocity. And let's say this is rotating as well. तो आगे भी जा रहा है, rotate भी हो रहा है. Let's say its angular velocity is let's use 3, okay? 3 radians per second. And let's say this is in the opposite sense, anti-clockwise sense. Okay, and let's say I have an axis over here. So what's RCA? So I'll explain those terms. Okay, so let's say I have an axis over here, and मुझे ये axis के about angular momentum निकालना है. Okay, so this is the formula for finding angular momentum about any fixed axis. This is the general result. Any axis, any fixed axis. In fact, अगर fixed भी नहीं है, then theoretically what it means is अगर तुम उस axis पे बैठोगे, तो बस ये जो velocity होगा वो relative velocity हो जाएगा. उसके frame में फिर again वो fixed axis की तरह दिखेगा. So even if it's a moving axis, you can still apply it about that. Just sit in the frame of that axis, and then that velocity becomes relative velocity. But you won't as such need to do it for a moving axis. But this is a very useful tool to be able to apply this about any fixed axis. So let's say there's an axis which is fixed ground के frame में. अब first term अगर तू देख रहा है, this is a very simple term. ICM निकालना आता है सीधा form. For instance, इस case में अपना ICM, given that it's a hollow sphere, is going to be 2 by 3 mr square, right? So m is 2 and r is 3, so 2 by 3 mr square omega bar. Okay, so remember, this is a vector equation and this is vector addition. But again, the good thing is, यहाँ पे vector addition में you don't have to apply parallelogram law, because there are only two angles possible between these two vectors. Okay? This term will either be, these terms will either be out of the plane or into the plane. They either have a clockwise sense or an anti-clockwise sense. So essentially, they're either in the same direction or opposite directions. So when we add them, if they're in the same directions, they get added up. They're in opposite directions, they get, maybe they cancel out, okay, or they get subtracted. So ये first term 2 by 3 mr square omega लिखते वक्त, I would always suggest कि just keep in track what the direction is. ठीक है? Either you could say in and out, or you could just stick to clockwise, anti-clockwise. Like for instance, this one is anti-clockwise. So I'm just going to make a note of that. Okay, anti-clockwise.
So how do we mention the direction in vector form? Like anti-clockwise or clockwise?
So anti-clockwise technically is going to be towards you. So you just represent it by this symbol. Are you aware of those symbols?
No, like I cap, J cap.
So that I cap, J cap, that depends if you have already defined an axis. तो axis define करोगे, then you can write an I cap, J cap. तेरे को हर सवाल में अगर बैठ के define करना है, then you can say कि towards you is Z. ठीक है? And accordingly, then towards you will be K cap. Okay? But again, you can just keep it simple. You can avoid these axes and all. You can just even just clockwise. You just want to check whether यार ये add करना है या subtract करना है. ये दोनों terms same sense में या opposite sense में. So you can just draw the sense as well, clockwise या anti-clockwise. ये वाला term, अब ये वाला term के लिए you'll notice कि this is very similar to, you've not learned angular momentum due to a particle as well, right? नहीं सीखा ना? अच्छा नहीं सीखा, ठीक है, okay, no worries. अच्छा, can you see that this term is very similar to R cross F? Torque is R cross F. Huh? Torque का definition की तरह है. Okay, so what is behaving as F? MVCM. ठीक है? So जैसा तुम्हें R cross F निकालना आता है, वैसे ही ये term को भी तुम evaluate कर सकते हो.
So MVCM, so like it should be linear momentum, right?
हाँ हाँ.
MVCM.
हाँ.
F is force.
नहीं, so I'm just saying कि this equation, ठीक है? You have seen a cross product equation before. One is position vector and one is some quantity. And what I'm trying to elaborate over here is, तुम्हें force के कारण torque निकालना आता है. कैसे निकालते हो force के कारण torque? अगर ये मेरा axis है और यहाँ पे मेरे पास एक particle है, ठीक है? और वो particle पे हमने कुछ तो force लगाया, let's say force is F, ठीक है? Particle का position vector is R, right? And technically we are supposed to perform a cross product, but ultimately what does that cross product result in? जब तुम cross product लोगे, R F sin theta वगैरह आएगा, and ultimately R sin theta, does that not become this perpendicular distance? तो how do you find the torque? तुम force को आगे पीछे extend कर सकते हो, आगे पीछे extend करने के बाद तुम ये perpendicular distance निकालते हो, right? And then you just say कि torque, and you call this perpendicular distance the lever arm, and then you say torque is lever arm into my force, right? Right? तो यहाँ तो वो जैसा किया लीवर आर्म इनटू फोर्स, सेम चीज अब यहाँ पे लगने वाला है. सो फॉर अ particle, this is again what I mentioned in the last class, and Shiv was already there, so I'm not fully revisiting that, but particle के लिए angular momentum का ऐसा formula है for a particle, ठीक है. And if you can see, then we stress कि यार ये तो एकदम similar ही term है यहाँ पे, similar ही equation दिख रहा है, which means finding an angular momentum due to a particle's linear momentum is just as easy as finding the torque due to a force. So imagine I have this particle over here which is moving with a linear momentum mv. वही same फंडा है, तुम उस linear momentum को आगे पीछे extend कर लो. Cross product would ultimately become, if this is your position vector, cross product would ultimately become that perpendicular distance into that linear momentum.
Excuse me, sir.
हाँ बोल.
So a particle has no angular momentum about itself, right? Or any axis horizontal to it?
So you're saying does it have an angular momentum about itself?
Or
So
that
उसमें-
dotted green line?
or that dotted green line, the answer is no. So about itself, तो obviously r bar ही zero है, and even about any point over here,
Then
the angle,
sine theta is 0.
yeah, sine theta is 0. R and P are either parallel or anti-parallel. ठीक है, it will not have any angular momentum. See? You can also just understand, so to give an understanding of what angular momentum in a way implies. So अगर यार इस एक्सिस के अबाउट तुम अगर पार्टिकल का मोशन देखोगे ना, in no way can you imagine it to be rotating about this axis. वो बस एक्सिस से या तो दूर जा रहा है. I just realized it's not very. Are you able to see all of this clearly?
Yes, sir.
ठीक है, तो या तो एक्सिस से दूर जा रहा है या एक्सिस के पास आ रहा है, राइट? तो in no sense is it, you can even imagine it to be rotating around the axis. So that in a way is what angular momentum in a way tries to measure. Like
If
in a
this
way it's
particle
trying-
was in rotation about.
if it was rotating above the axis, it's trying to, in a way measure ये motion में rotation कितना है, loosely speaking. ठीक है, इस axis के about rotate हो रहा है. Can you guys tell me, मतलब if you were to just see this part of the motion, would you say the rotation of that particle above this axis is in the clockwise sense or the anti-clockwise sense?
Clockwise.
Yeah, clockwise.
सबको दिख रहा है clockwise?
For them we
हाँ, so just imagine if it has to complete a round, complete a circle around the axis, it would have to rotate like this. Okay? So that's the. So वहाँ से direction तो बहुत easy है, तुम्हें सीधा इधर ये हो गया तुम्हारा magnitude, direction बहुत easy है. Coming back to this term, in general for an extended body, notice the only difference. एक तो P के जगह momentum, linear momentum of the body हो गया, जो है mvcm, obviously, ठीक है? But R के जगह RCM हो गया. मतलब ये जो mvcm वेक्टर यहाँ पे लीनियर मोमेंटम कहाँ प्लेस कर रहे थे? पार्टिकल के पोजीशन पे, राइट? एंड देन वी डिड द रेस्ट. वही अब यहाँ पे mvcm कहाँ पे प्लेस करना है? किसी के पोजीशन पे. किसके पोजीशन पे? सेंटर ऑफ मास की पोजीशन पे, which you anyways will do, right? You will draw vcm at the center. So it's very simple. तुम ये लीनियर मोमेंटम वाला वेक्टर को सेंटर ऑफ मास पे ड्रॉ कर लो, फिर यहाँ से एक
So
हाँ बोल.
why did you add a moment of inertia in the first formula and not in the second formula?
Hey, this is the result. This is, we can derive this result. थोड़ा लंबा derivation है, but I
No,
can.
but what's the difference between both the formulas? Like वो जो नीचे formula है, angular.
हाँ, this is just for a particle. So this is actually the complete formula. You can imagine कैसे particle के लिए ये term गायब हो जाएगा, because a particle has no moment of inertia about itself. So even if it is rotating, that's insignificant. इसलिए particle और RCM के जगह मतलब छोटा ही है तो R of the particle हो जाता है. VCM के जगह V of that particle हो जाता है.
So basically for a particle, angular momentum is same as linear momentum. Right?
Same कैसे हो गया? Linear momentum is only that part. समझा ना? हाँ. तो ये जो ऊपर वाला रिजल्ट है वो पार्टिकल का भी रिजल्ट देता है.
So it's covering an an angle, right? The particle is covering an angle.
Covering an angle मतलब?
वो जो नीचे diagram है,
हाँ,
is it covering an angle?
पार्टिकल इधर है,
हाँ,
पार्टिकल सिर्फ मूव कर रहा है और कुछ नहीं कर रहा है,
linearly move कर रहा है.
लीनियरली मूव कर रहा है, और उसके मोशन के कारण हम इस एक्सिस के अबाउट एंगुलर मोमेंटम निकाल रहे हैं, एंड दैट इज डिफाइंड एज its position vector cross its linear momentum.
So angular momentum should form an arc, right?
नहीं, no need for that. Angular momentum is defined at an instant. You can just take a snapshot and also figure out the angular momentum. ये तो this is all not part of the, ये हो this is all not part of the diagram. ये हो गया पार्टिकल का position vector cross momentum. वो साइन थीटा को के साथ कैसे डील कर रहा है, आर साइन थीटा, ये टर्म हो जाता है जैसे टॉर्क में, ठीक है. Alright.
We can imagine the particle is attached to the axis, just like torque के केस में हम लोग we imagine like axis is fixed.
हाँ.
It's the same thing with torque and
जैसा the way you find the torque due to a force, the same way you find the angular momentum due to a linear momentum. तो यहाँ पे बस सेम चीज, वहां पे कैसे p को आगे पीछे एक्सटेंड किया, वैसे यहाँ पे इस वेक्टर को आगे पीछे एक्सटेंड कर लो, तो ये हो गया, उसको आगे पीछे एक्सटेंड कर लिया, ठीक है. वेक्टर को कहाँ पे प्लेस करना था, सेंटर ऑफ मास पे प्लेस करना था. एनीवेज यू डू दैट. तो यही मोमेंटम को आगे पीछे एक्सटेंड कर लो एंड देन फाइंड दिस परपेंडिकुलर डिस्टेंस. तो ये आ गया परपेंडिकुलर डिस्टेंस. लेट्स जस्ट से कि इस क्वेश्चन में दिस इज जस्ट रैंडमली सेइंग कि दिस इज, लेट्स से दिस इज 4, ठीक है. तो ये सेकंड टर्म कितना हो जाएगा, परपेंडिकुलर डिस्टेंस 4, राइट, इनटू mv. तो m is 2, velocity is also 2. That's it. Perpendicular distance into linear momentum. All right. So there's another term, and that term is 4 perpendicular distance into linear momentum. Mass 2 kg, velocity 2 meters per second. बस अब ये जो टर्म है, ये टर्म किस सेंस में, कैन यू जस्ट फिगर आउट एक्सिस के अबाउट ये टर्म किस सेंस में? जस्ट लाइक दैट डायग्राम, क्लॉकवाइज दिख रहा है तुम्हें भी, है ना? तो क्लॉकवाइज है. सो अब बिकॉज ये क्लॉकवाइज है, टेक्निकली अब तुम्हें while combining them vectorially तुम्हें subtract करना पड़ेगा. Okay, so if I want the net anti-clockwise, कौन सा टर्म बड़ा हो सकता है? You can see that ये 4 है, this is going to be 4 into 9, right, 36, and this is going to be 16. So this term is bigger, right? So the one which is bigger will dominate. तो net result हो जाएगा 36 anti-clockwise plus 16 clockwise. 16 को उल्टा कर लो, या anyways you can see उल्टा कर लो और ऐड कर लो, तो -16 clockwise होगा, और फिर ये हो जाएगा 20, पूरा उल्टा बोल दिया, 20 एंटी क्लॉकवाइज हो जाएगा.
So उसमें यूनिट डार्ट,
which one?
RCM, वो जो L का value.
तो RCM, यार RCM क्रॉस MVCM becomes RCM, जैसे यहाँ पे R perpendicular into P है ना, वैसे ही becomes RCM perpendicular into P. That's what this term becomes. So this is this guy over here, this guy 4, that was the perpendicular distance. Okay, that was your lever arm. This next term is your mass, and the next term is your velocity of the center of mass. ठीक है, समझा? थोड़ा ये मतलब थोड़ा recap दिया. We practiced a little bit in the previous class. Just giving you this formula so that we can, you know, do what has to be done today. Cool. So copy करना था क्या? I would suggest keep your books out. Hi Vikrant. Hi Vishal. You guys online as well, I would just suggest keep your books out. I may not write everything on these notes. There's some things I may just dictate as well. So just keep your books out. Okay. So we're going to have a look at conservation of angular momentum. And we're going to start with this. Let's just derive this result. So let's start with a particle. And particle ke liye you can see by Newton's second law that the force acting on the particle, the resultant force on it, is the rate of change of that particle's linear momentum, right? So that's Newton's second law, right? Now, what we will do with both sides is, let's say this is our particle over here. ठीक है, ये अपना particle है और मान लो ये कोई तो एक axis है, some any axis of interest, can be any axis we want. So let's say ये particle का position vector from that axis is r, right? LHS and RHS are the same. I can really perform any operation on the LHS as well as the RHS, and it should still both sides should be equal, right? Because LHS is the same as RHS. So I'm performing this operation. R cross LHS is R cross RHS. Look at what that gives me. So that gives me R cross F, right? We know what that is. And on the right hand side, it gives me R cross dP by dt, right? And R being at an instant, of course, it's not changing with time. So you can take this. In fact, acha, yahan pe, now watch out for this.
So R is the perpendicular distance. Right?
R is the position vector of the particle. R is the position vector at any instant.
So it has to be motion. And if it's in motion, then R shouldn't it change?
हाँ, it will change. R will change. R will change. तो इसलिए ये देख लो, R will change with time. You're right. I can't just take it in. But अब यहाँ पे देखो. Let's see what dl by dt will give us. Okay. So L is what? Again, angular momentum. Angular momentum क्या है? R cross P. You're absolutely right. R will change. ठीक है? But now, if I differentiate this with respect to time, तो क्या करेंगे? Product rule लगाएंगे. Product rule क्या बोलेगा? बोलेगा dr by dt cross P, right? Plus R cross dP. So sorry. R cross dP by dt. ठीक है? अब देखो, इसमें look at this term. What is dr by dt going to be? Velocity. अच्छा, तो what will happen to velocity cross linear momentum?
No, sorry.
Anyone? Velocity cross
V square.
velocity cross linear momentum.
Zero.
Zero. Who was that?
So me.
Me.
Shiv.
Okay. Yes, zero. Q zero.
So because angle between momentum and velocity is zero. So
Yes. यार parallel vectors का cross product zero होता है ना? A cross A zero. AB sin theta. Theta is, as he said, parallel है तो zero angle है, right? So because they are parallel, उनका cross product is going to be zero.
blindly moving in the same direction.
एक ही बंदा है, दो बंदे नहीं, एक ही बंदा है, पार्टिकल है, पार्टिकल का जो भी वेलोसिटी होगा, वेलोसिटी और मोमेंटम पैरेलल होगा, राइट? तो वेलोसिटी क्रॉस मोमेंटम इज गोइंग टू बी 0. Correct?
The dot product will be mv square, right?
Dot product will be mv square, cross product will be 0. So यहाँ पे look at what we got, r cross dp by dt. We just proved that that is equal to dl by dt. All right, so right hand side बन गया dl by dt. Right hand side बन गया rate of change of angular momentum. And left hand side बन गया r cross f बन गया अपना torque.
It's 0 because of sine 0, right?
हाँ, पैरेलल वेक्टर्स का टॉर्क, पैरेलल वेक्टर्स का क्रॉस प्रोडक्ट 0 होता है. So we just prove for a particle that torque is dl by dt, rate of change of the angular momentum. In a way, it's, you can see how it's somewhat similar to this. Okay, very, very, very important result. So just like force is the rate of change of linear momentum, torque is the rate of change of your angular momentum. Okay. And for an extended body, so you again have the same result. So extended body के लिए बस इसी को add करेंगे हर particle के लिए, right? So for an extended body, what we'll have to say is we'll add up the torque for each particle, right? Each particle का torque is the rate of change. Each particle का torque is the rate of change of that particle's angular momentum. Each particle ka torque is the rate of change of that particle's angular momentum. So if I just add this for every single particle of the body, okay, so you know how summation works with differentiation. The right hand side will become d by dt of summation li. And adding up the angular momentum of every particle is going to give you the angular momentum of the entire body. Pura body ka angular momentum mil jayega. So right hand side again becomes dl by dt for the entire body. The only thing over here is what do you
There are a lot of small number of particles, right? So why did you integrate?
अरे एक मैं ऐड ऐसा बैठ के ऐड नहीं कर रहा हूँ, ये थियोरेटिकली ऐड कर रहा है. We don't have to, of course, integrate भी कर सकते हैं, but ये बस theoretically बोल रहा हूँ. Yeah, I'm just theoretically imagine, if you're not physically adding them. Just imagine you're adding this for each and every particle, adding up all the torques gives you, well, all the external torques acting on the body plus all the internal torques, right? So external torque will be particle पे बाहर से जो लग रहा है. Internal torque will be particle एक दूसरे पे जो लगा रहा है. Then obviously you know कि internal torque cancels out. So you're left with just the external torque. नहीं, internal torque always cancels out. Always cancels out. ये rigid के लिए नहीं है. नहीं, rigid body के लिए भी internal force cancels out.
What's the condition for rigid force? Rigid body?
Rigid body के लिए the separation between any two particles cannot move. So I think what you are mistaking is work internal is 0 only for a rigid body. Work internal is 0 for a rigid body. A rigid body cannot do work on itself. But internal forces have to cancel out. Internal torque also cancels out. ये internal forces cancel out वो तो वहां से आता है अपना न्यूटन्स थर्ड लॉ से ही आता है. एक A ने B पे जो डाला B ने A पे उतना ही डाला. EXT external internal. हाँ वही वही T है. Okay.
But we can integrate also, right?
हाँ integration sign डाला है. Can integrate as well. ये basically just saying कि theoretically you add this up for every particle, you will prove this result कि एक extended body के लिए external torque is the rate of change of its angular momentum. Just like external body के लिए आता है F external is mvcm. F external is rate of change of mvcm. F external is dp by dt. ठीक है. True for all bodies. ये confusion नहीं होना चाहिए. So I'll just say true for all bodies. The pivotal law है. In fact, this being true for non-rigid bodies is what leads to very interesting applications.
So torque in external and torque internal is like more.
हाँ, torque internal adds up to 0. Torque internal is the, so we are adding up the torque on each particle ना, तो particle A particle B पे लगा रहा था और फिर particle B भी particle A पे लगाएगा. So this is the addition of all those torques and they cancel out. This is the torque on particle A from forces outside the system. And those torques remain. Yash, you were physically present, right, last time? Never mind. Cool. So statement लिख लो. With that, लिख लो the statement of conservation of angular momentum. So लिखो if a body experiences no external torque, if a body experiences no external torque about an axis,
No external.
if a body experiences no external torque about an axis, its angular momentum is conserved about that axis. Its angular momentum is conserved about that axis. This is called as the principle of conservation of angular momentum. This is called as the principle of conservation of angular momentum. Okay. So what it's saying is if torque external is 0, and we know that torque external is dl by dt, So if torque external is 0, then L should be constant.
When a torque internal is 0, that's only angular momentum. This statement.
अरे नहीं यार, टॉर्क इंटरनल तो 0 होगा ही, वो कैंसिल हो जाता है
हाँ,
एक पार्टिकल के मतलब,
what?
ठीक है, वो तो आपस में कैंसिल होता ही है. अगर एक्सटर्नल टॉर्क नहीं है, बाहर से कोई एक बॉडी पे टॉर्क नहीं लगा रहा है, तो टॉर्क एक्सटर्नल, व्हाट हैव वी प्रूव्ड, टॉर्क एक्सटर्नल इज dl by dt. सो अगर टॉर्क एक्सटर्नल 0 होगा, अगर टॉर्क एक्सटर्नल 0 होगा, तो व्हाट विल L बी? कब उसका डेरिवेटिव 0 होगा? किस चीज का डेरिवेटिव 0 होता है? समथिंग
Constant.
which is constant, right? So L will be constant with respect to time. L will not change with time. So if torque external is 0, then the angular momentum of that body will have to be constant. ठीक है, कोई एक एक्सिस के अबाउट टॉर्क अगर 0 रहेगा, तो एंगुलर मोमेंटम उस एक्सिस के
Excuse me, sir.
अबाउट. हाँ बोल शिव.
Sir, can you give an example where there's a torque about one axis but no torque about another?
हाँ, so I mean, so very, so let's not list that down, but many simple examples. For instance, मान लो एक ऑब्जेक्ट गिर रहा है with velocity v. ना तूने ही बताया कि यार अगर हम इस एक्सिस, उसी लाइन में एक एक्सिस लेंगे तो उसके बाद टॉर्क 0 होगा, राइट? बट और कोई एक्सिस लेंगे तो उसके बाद टॉर्क 0 नहीं होगा.
Oh, okay, understood. So, but
So-
if there's a net force on the body and it's an extended body, and the axis is internal to the body, then there'll always be a torque around that axis, right?
Again, not necessary ना. See, x तू बोल रहा है कि there's ये extended body है, extended body पे एक net force लग रहा है, ठीक है? And you take an axis inside the body. Again, I can take an axis along this line itself. So if I'm
Understood. Sir.
okay, so torque, it's very easy to somehow find an axis जिसके बाद torque 0 होगा, when especially when the net force is non-zero.
So angular momentum is equal to constant. Just means that it's constant.
Yeah. So हाँ, okay. Shiv, yours is answered, right?
Yes, sir.
और आगे हम यूज करेंगे, वी सी हाउ वील, है ना, ऐसा बहुत क्वेश्चंस देखेंगे जहाँ पे कोई भी रैंडम एक्सिस लोगे तो उसके बाद टॉर्क रहेगा, पर हम इंटेंशनली वो एक्सिस ढूंढेंगे जिसके बाद टॉर्क 0 है, so that we can conserve angular momentum. And angular momentum is constant, basically means the initial angular momentum of that system is equal to the final angular momentum of that system. That's what it means. ठीक है?
So basically, linear momentum के case में it was like during collision,
हाँ.
the momentum like it's transferred. But in case of angular momentum, how will it like get transferred?
हाँ, so देखते हैं. So let's see one example. So for अब examples देखते हैं, थोड़ा इसका feel लेके आते हैं. So one example is figure skating, है ना? So you've seen those people, Olympics वगैरह में देखा होगा, they skate on ice and then they whirl and do all sorts of stunts. देखा है?
Yes.
हाँ. So while skating, like one trick that they would use to suddenly increase the speed is, imagine they are first standing like this, ठीक है? This is their initial pose, ठीक है? तो यहाँ पे let's say they have some angular velocity, ठीक है? ω1. But then what they do is, I'm not sure if I can draw this, but they pull their arms inwards, ठीक है? पहले हाथ is extended, ठीक है? Never mind. तो पहले हाथ को बाहर extend करते हैं, फिर उसके बाद they pull their hands inward, ठीक है? And even they try to shrink, although the shrinking makes no difference, but they will essentially fold their hands.
Also during swinging, like using our legs, we do that as well, right? So like if we swing SLX for like the speed.
Yes. Perfect. तो यहाँ पे like perfect. That has the same effect as this. ये करने के कारण क्या हो रहा है? What are they effectively changing? So if I look about their axis, okay, if you look about their axis, angular momentum about this axis is going to be I omega. Okay, maybe that's another thing. Since you guys missed the previous lecture, I can just illustrate again. So if you go back to that formula, I mentioned that formula that we had about in general any axis has two special cases. You can say angular momentum about the center of mass is ICM omega. Okay, and similarly angular momentum about a term called as the instantaneous axis of rotation. डरना नहीं है उससे. Instantaneous axis of rotation is basically the fixed axis about which they are rotating at a particular instant. Okay, so angular momentum about those two, they are special cases of that general formula.
It's changing with time, right? The axis.
It could be changing with time, it could be at the same position. It just means that at this instant there is some axis, and us axis के about L is I omega और center of mass के about भी L is I omega. ठीक है? So this इस बंदे का अगर L देखोगे एंगुलर मोमेंटम उसके सेंटर मास के अबाउट, ठीक है, तो पहले कुछ तो मोमेंट ऑफ इनर्शिया था उसका, ठीक है. हाँ बोलो. हाँ, सो यार एक तो इसमें RCM क्रॉस MVCM L अबाउट द सेंटर ऑफ मास जब निकाल रहे हो तो RCM itself becomes 0. Position of the center mass with respect to the center mass, that itself becomes 0. ठीक है, एंड इसको तो डायरेक्टली भी डिराइव कर सकते हैं. वो फॉर्मूला से आना है तो यू कैन अप्लाई पैरेलल एक्सिस थ्योरम एंड यू गेट दिस रिजल्ट. सो ऑल दिस वाज बेसिकली कवर्ड इन दैट क्लास, बट कमिंग बैक टू दिस, ठीक है, तो एंगुलर मोमेंटम सेंटर ऑफ मास के अबाउट क्या है, अभी फिक्स्ड एक्सिस के अबाउट आई ओमेगा है. ठीक है, आई ओमेगा. तो नाउ ट्राई टू अंडरस्टैंड व्हाट्स रियली हैपनिंग. पहले उसका एंगुलर मोमेंटम I1 ओमेगा 1 था, ठीक है. अब उसका एंगुलर मोमेंटम I2 ओमेगा 2 है, राइट. एंड वी नो कि इज देयर एनी एक्सटर्नल टॉर्क अबाउट दिस एक्सिस? हाँ, इट्स ऑलमोस्ट मिनिमल बिकॉज ये आइस स्केटिंग है ना, तो देयर इज वेरी लेस फ्रिक्शन इन्वॉल्व्ड. सो टॉर्क एक्सटर्नल is in this example it's going to be 0, right, close to 0. ठीक है, just ideal world देख रहा है.
Friction was there, how will it exert torque? Like
वो तो पैर पे लगा सकता है. ये बंदा घूम रहा है, ऐसा घूम रहा है, तो फ्रिक्शन इस पे एक इस डायरेक्शन में फोर्स लगा सकता है और इस पे एक अंदर की तरफ फोर्स लगा सकता है, एंड उसके कारण टॉर्क बिल्कुल आ सकता है, राइट. इनफैक्ट इफ in the real world if this guy tries to spin like this, his speed will eventually decrease, and that's because of friction. So torque external, but ideal world में 0 है या real world में भी it's close to 0, जिसके कारण initial angular momentum is the final angular momentum. So now can you make sense of why his speed finally is greater? Why is it greater? What is happening? What is he doing by pulling his hands inward? क्या अचीव कर रहा है वो? Changing the moment of inertia. So is he increasing it or is he decreasing it?
Because they're directly proportional, right? No, oh yeah,
he's decreasing it. Moment of inertia is mr square. वो r को कम कर रहा है, right? So because I1 is lesser than I2 omega, because I1 is greater than I2.
Inversely proportional, right? Angular speed and
हाँ, precisely. So L, I and omega का प्रोडक्ट सेम है, because वो I अब कम कर रहा है तो omega उसका बढ़ रहा है. Okay, so his final angular velocity is greater. So this is, you know, this is what he's doing. तू भी जो swing का बोल रहा था, है ना, तो swing में भी क्या है, at any instant, ठीक है, at any instant just by pulling your legs away from the ground, you're basically reducing the moment of inertia about the axis. You're reducing that moment of inertia, and thereby you're increasing omega above that axis. There are more interesting examples. You can just maybe note this.
One second.
So, oh wow, oh but that worked interestingly.
So the advanced में how do they test these concepts?
अरे इसको देखेंगे, ये तो सिर्फ ये थियरी अब समझ में आ रहा है हमें. We see how we can work with questions and all. So I'll just to write a phrase like pulling the hands inwards. Pulling the hands inwards decreases the moment of inertia.
If he's decreasing his like radius or moment of inertia, that means linear velocity will also decrease because he's decreasing the radius, right?
And thus, एक second, and thus increases omega. Yeah, see. तू क्या बोल रहा है वापस बोल?
So ये ऐसे करके like while he's
omega बढ़ गया, हाँ.
हाँ. So that means he's decreasing the linear velocity, right?
कहाँ से linear velocity? उसका center of mass हिल ही नहीं रहा है. मान लो ऐसे ही जगह पे खड़ा होके वो spin कर रहा था.
नहीं, not that linear of velocity, circular linear of velocity.
तो मतलब उसके कुछ finger tip का ध्यान दे रहा है and you're probably commenting on the linear velocity of his fingertips.
Like वो formula था ना, omega is equal to b by r.
हाँ. तो यहाँ पे अब ये पूरा बॉडी का ओमेगा है, बॉडी का हर पार्टिकल घूम रहा है, which is not of great importance to us, right? उसका center of mass हिलेगा, so then that's maybe something significant. But you're right, हाँ वो
no, it's not because they are directly proportional.
So pulling the hands inwards decreases I and thus increases omega. Yeah. Then just another example, and then we'll move to questions. So I don't know if you watched the sport freestyle motocross. It's when you have these people who perform stunts with dirt bikes. Okay, so they'll ride off a small hill and they'll try to perform a flip or something like that. Right? कभी खेला होगा वो game या देखा होगा. So how do they do that? How do they perform a flip? Because if you think about it, once you're in the air, है ना, just by saying कि अरे चलो I'll start rotating now, you can't make yourself in the entire bike turn just by deciding to. Why? There's no external torque. जो भी तुम कर सकते थे, maybe you could have done while you're on the ground. But now once you're in the air, there's no external torque about the entire system's center of mass, right? So for you to start rotating, you need an external torque about the center of mass. So then
don't they lean?
Don't they lean? Are you saying the person leans backward and फिर वो
This is
leaning?
when the center of mass changes.
So, अच्छा, So even if he leans backwards, is there any external torque about the
No,
center of
sir.
mass?
No external.
है ना? No external torque about the center of mass.
He
So
just rotates, right?
तो वही मैं बोल रहा हूँ अब ठीक है just so he's
If he's rotating, then the center of mass will not change.
from where does he get that once he's in the air? We're talking about a person जो let's say he's gone off the hill,
Yeah.
ठीक है, and as he leaves the hill his bike only has a VCM, उसका बस center of mass का कोई velocity है but omega नहीं है, ठीक है. Now mid air he decides to do a flip. How does he do that? According to physics, just by deciding to start rotating you cannot rotate. Why? Because you need an external torque, है ना? क्या है? Torque about the center of mass
So he uses his muscular force as well.
will give you rate of change of angular momentum about the center of mass. तुम सोचो एक second what you're saying. Torque about torque external about the center of mass, है ना? है कुछ external force. Just by rotating you can't. तो तुम क्या करोगे? तुम बाइक तुम ऐसा पीछे लीन करोगे, तुम बाइक को ऐसा खींचने की कोशिश करोगे, बाइक तुम्हारा हाथ को नीचे की तरफ खींचेगा, ठीक है. So you can't really start rotating just by deciding to do that or wanting to do that. But interestingly, what you can control once you're in the air is you can control these wheels. All right. So what actually happens is let's say this guy wants to do backflip. उसको अब मान लो ऐसा घूमना है, तो क्या करता है व्हील्स के साथ? वो बाइक को एक्सेलरेट करता है. तो एक्सेलरेट करने के कारण ये जो व्हील है this starts rotating faster. Now as this rotates faster, net angular momentum should have been conserved, है ना? तो तुमने एक कंपोनेंट का एंगुलर मोमेंटम इस डायरेक्शन में बढ़ाया, तो बचा हुआ कंपोनेंट्स का एंगुलर मोमेंटम इस डायरेक्शन में बढ़ेगा, so that the overall angular momentum stays zero or stays whatever it was initially.
So can you explain again?
हाँ, वापस बोल देता हूँ. So torque external is dLCM by dt and torque external about the center of mass is zero, right? So therefore because external torque is zero, therefore center of mass के about initial angular momentum is center of mass के about final angular momentum, ठीक है. अब initial angular momentum में कौन रहेगा? मतलब इसमें आदमी का angular momentum, ठीक है. Initially let's just write all the components, ठीक है.
So of the man plus the bike.
हाँ, man plus bike को एक साथ ले लेते हैं. So let's say man.
What's the relation between angular momentum and angular acceleration?
We'll come to, ठीक है, I'll talk about that, but not relevant to this question, no? Because
if he's changing the acceleration,
हाँ,
that's how he's changing the angular momentum, right? You told just now, right?
हाँ. So let me just एक बार वापस सुन ले what I said, ठीक है. So ये let's say man plus bike का initial angular momentum plus वो wheel का angular momentum initially, ठीक है, is equal to man plus bike का final angular momentum plus wheel का final angular momentum. Okay. अब देखो man plus bike का initial angular momentum, let's say that's zero, right? Starting में when he launched off.
So if you increase the angular momentum of the wheel, the bike will turn in the opposite direction.
Perfect. Got it?
Got it, sir.
हाँ. तो ये क्या हो रहा है? Man plus bike का initial angular momentum मान लो zero है. He launched off the hill, ठीक है? They are not rotating then. ये wheel का कुछ तो था. Wheel का कुछ तो angular momentum था. Let's just say this is let's say angular velocity omega 1 था, ठीक है, and clockwise था. Wheel was rotating clockwise. अब वो इसको बढ़ा रहा है. इसको बढ़ा रहा है, इसको बड़ा कर दिया, ठीक है। तो इसको बढ़ाने के कारण अब ओवरऑल तो सेम होना चाहिए एंगुलर मोमेंटम, तुम क्लॉकवाइज वाले एंगुलर मोमेंटम को बढ़ाओगे, ओवरऑल सेम होने के कारण some other parts should start rotating in the anti-clockwise sense. So that's how the bike and the man managed to rotate in the opposite sense, and that's how you perform a backflip.
Yeah, so that's what I was asking. कि उसने angular acceleration increase किया, that's how
हाँ
omega changed, and
हाँ
that's how
हाँ
angular motion.
हाँ. So in a way, like जो बाइक का मोटर इस व्हील को इस सेंस में अल्फा दे रहा है, क्लॉकवाइज सेंस में अल्फा दे रहा है, वही व्हील उस मोटर पे एंटी क्लॉकवाइज सेंस में अल्फा, है ना, एंटी क्लॉकवाइज सेंस में टॉर्क दे रहा है, and that torque is then causing the motor which is attached to the bike, and the man is sitting also rigidly on it, that's causing these guys to rotate in the opposite sense.
No, but like wheel के case में, if you're talking about the wheel's rotation, it's rotating about itself, right?
Huh, fair enough. So angular momentum, but still about the center of mass, the body is still defined for all particles, irrespective of whether they're rotating about the center or they're rotating by themselves. That's what that ICM omega wala term takes into account. L is ICM omega plus RCM cross MVCM. ICM omega takes into account वो खुद के about क्या rotate कर रहा है, and RCM cross MVCM takes into account उसका center इस axis के about कैसा है, कैसा rotate कर रहा है. So imagine the earth is moving around the sun, ठीक है, earth का angular momentum over the sun would be a combination of both. The ICM omega will take care of the rotation of the earth about its own axis, and the RCM cross MVCM will take care of the revolution of that axis around the sun. Okay, so when we talk about this angular momentum being conserved for this entire system, सबको system में ले लिया ना, so that's the sum of all these angular momentums. Wheel चल रहा है, उसकी खुद के about rotate कर रहा है, तो फिर भी center का of mass of the system के about कुछ तो angular momentum है उसका, वो तुम और बढ़ा रहे हो when you cause this wheel to rotate in the clockwise sense faster. See?
So if the wheel is rotating, then पूरे bike का angular momentum कुछ initially है. That's what I'm saying.
पूरा हाँ, man plus bike including the wheel system का कुछ तो मान लो angular momentum initially है because of the wheel, और तुमने wheel का और बढ़ा दिया, ठीक है, मान लो initially 10 था, तुमने wheel का 20 कर दिया clockwise, तो इसका 10 एंटी क्लॉकवाइज होना चाहिए ताकि कुल मिलके 20 minus 10 10 क्लॉकवाइज अभी भी रहे. That's the idea.
Excuse me, sir.
हाँ बोल.
So then how do cyclists do flips? Because a cycle, you can't turn the wheels backward.
Have you tried doing it on a cycle?
No, sir.
साइकिल्स का भी वो रैंप पे होता है ना,
हाँ,
रैंप से ऊपर जाके वापस फ्लिप करके नीचे आते हैं, उसमें
so I do know कि cycle में if you want to do a wheelie or something like that, you have to give a sudden jerk देना पड़ता है, you have to pedal पे, so you're suddenly increasing, again you're suddenly trying to increase the angular momentum of the rear wheel in the clockwise sense, which helps the rest of your cycle, if it's light enough, rotate in the anti-clockwise sense. So my guess is, again, if you're in the air and if you don't already have some angular momentum while you're in the air, the only way, even if a cyclist has to perform some flip, is to manipulate how the wheels are rotating. He could try pedaling midair.
But वो wheel, if it rotates with a higher angular velocity, the moment of inertia will be like it will be the same, right, for the wheel, because it's rotating about its own axis.
ठीक है, moment of inertia change नहीं होगा, it's fine, but omega बढ़ाने के कारण overall angular momentum तो wheel का बढ़ा सकते हो, ठीक है, जिसके कारण सिस्टम का सेम होने के लिए बचा हुआ चीज बैकवर्ड जाएगा. शिव, I hope I answered your question. You could still pedal.
Yes, sir.
When you're in the air, you can pedal and then do these things. ठीक है, don't try this at home. But this is just theory. I don't know how it works practically. कितना easy होगा. All right. कुछ लिखना था या we can move on. देखो. So let's do an example. Let's say कि see a disk of mass m, radius r, was rotating about its rather about its axis on a smooth horizontal surface. It's rotating about its axis on a smooth horizontal surface with angular velocity omega. Okay, with angular velocity omega. A disk of mass 2m and radius r is placed on top of it. Okay. Okay. So there is friction between these two guys. Okay? There is friction between these two disks. So find the final omega, find the final angular velocity with which the two will rotate. Find the final common angular velocity with which the two rotate. So there is sufficient friction between the two disks. Okay? So that friction is going to eventually prevent those two surfaces from slipping on each other. Okay, so this was one disk. Okay, and this was rotating about its axis with an angular velocity omega. Okay, on a smooth frictionless floor. उसके ऊपर तुमने एक और डिस्क प्लेस किया. ऊपर वाले डिस्क का मास 2m है, इस वाले का मास m है. ऊपर वाले डिस्क का ओमेगा 0 है, उसको इसके ऊपर प्लेस कर दिया. तो प्लेस करने के बाद क्या उनका कॉमन ओमेगा होगा, and also find the loss in kinetic energy.
Angular momentum will be conserved, right?
Yeah, so there is no, so there's the whatever axis they're rotating about, uske about torque nahi, if frictionless floor hai, so torque external will be 0.
So radius is the same for both disks, right?
हाँ, radius दोनों का r है. Oh. Just check the chat. Shiv, your first answer is correct.
Oh, so I have a mistake in my second one.
Just cross check that.
So in these questions, they will not give the moment of inertia.
No, they won't. You'll have to remember those results. You, हो गया? अच्छा.
So can you check now?
हाँ अभी सही है. अभी सही है. So, do you guys understand? Acha, how does this relate to conservation of angular momentum? Does this meet the criteria? Torque वगैरह zero है क्या?
Yes, sir.
Okay. तो यहाँ पे just notice कि torque external is zero because there's no friction, right? So friction नहीं है. Friction with the ground is zero. ठीक है?
Question, but moment of inertia याद नहीं आ रहा.
अच्छा mr square by 2 होता है डिस्क का.
Is it a 3D disk or a 2D?
Doesn't make a difference. क्यों फर्क क्यों पड़ेगा?
अच्छा हाँ, yes, sir.
By the way, Shiv, I think थोड़ा गड़बड़ है आंसर में. Just check कर वापस. Moment of inertia सही यूज करके देख ले. Friction with the ground is zero. ठीक है? जिसके कारण there's no one who can apply an external torque. So if I take both discs as my system, ठीक है? मेरा सिस्टम क्या है? दोनों डिस्क को ले रहा हूँ सिस्टम के अंदर. So if my system is both the discs, then the only external torque that could be acting would have been friction. There's no external torque. There's no friction. बाहर से उनकी आपस में है. उनके आपस में तभी एक स्लो डाउन हो रहा है, एक स्पीड अप हो रहा है. Right? But external torque नहीं है. External torque नहीं है मतलब angular. अच्छा किसके about? I'm going to choose which axis. So I'm going to choose this axis. ठीक है? The central, the axis, the center of mass. ठीक है? या this also the instantaneous axis of rotation. ठीक है? Axis passing to the center. So torque external about, maybe I'll just write center of mass is 0.
Will m slow down or will it speed up in terms of angular velocity?
So what do you think? अच्छा, see, let's imagine कि एक rotating disk है. एक rotating disk के ऊपर तुम एक और disk डालोगे.
It's gonna slow down. Right?
It's go. हाँ. So what will happen is friction does not like this slipping. So friction will do what it can to oppose that slipping. Friction between the lower disk and the upper disk. तो वो lower disk को slow down कराएगा, upper disk को speed up कराएगा. Lower disk का ओमेगा कम करेगा, upper disk का ओमेगा 0 है ना, बढ़ाएगा, ताकि दोनों साथ में घूमे. वो फ्रिक्शन का ऑब्जेक्टिव है. It does not like relative slipping between these two. So it wants both the layers to move together. Right?
तो दोनों opposite direction में घूम रहे हैं कि same direction?
Starting में ये रेस्ट पे था, ये घूम नहीं रहा है और नीचे वाला घूम रहा था.
अच्छा.
ठीक है, और डाल दिया.
तो यहाँ पे तो हमें दो वेरिएबल्स और एक ही इक्वेशन रहेगा.
कौन से दो वेरिएबल्स है? देख, ओमेगा सब दिया है.
फाइनल में ओमेगा लाइक उसका दोनों का ओमेगा चेंज होगा.
नहीं, तो यहाँ पे find the final angular velocity with which the two rotate. That means that's a common angular velocity. Friction has done its job of bringing them together. So they're now rotating with a common angular velocity. All right. So torque external is 0 about the center of mass. Yeah, about the IAOR. And let's use that word more often. So torque is 0 about its instantaneous axial rotation. ठीक है, जिसके कारण initial angular momentum about that same axis is the final angular momentum about that same axis. Initial angular momentum about the IAOR, मतलब center वाला axis जो rest पे है, is तो जिस lower वाले disk के कारण होगा mr square by 2 into omega. Very nice. और फिर finally क्या होगा? दोनों के कारण, now both of them are rotating together, right? So अगर final angular velocity omega dash है तो एक mr square by 2 omega dash और दूसरा 2mr square by 2 omega dash, या उनके angular moments of inertia को club भी करके रख सकते थे, 3mr square by 2 omega dash. So from this equation mr square by 2 काट दो and you can see that omega is equal to 3 omega dash. ठीक है? So omega dash is omega by 3. It's very similar to, है ना, एक particular mass m is moving with some velocity, उसके ऊपर 2m mass का particle वापस बैठ गया, inelastic collision की तरह हो गया, तो mass 3 गुना हो गया तो velocity 1/3 हो जाता है. वैसे ही क्वेश्चन है, यहाँ मोमेंट ऑफ इनर्शिया 3 गुना हो गया, ओमेगा डैश 1/3 हो गया. यहाँ तक ठीक है?
मेरा ओमेगा डैश इज इक्वल टू 2 ओमेगा आ रहा है.
ये इक्वेशन है ये इसमें क्या किया तूने? mr square by 2 omega plus mr square by 2 omega dash
2 mr square by 2. Yeah, so 2 cancel. Then 2 mr square.
ये टर्म भी तो है, तूने ये टर्म नहीं लिखा होगा. एक मिनट.
Yeah. So
तेरे को आ गया ना?
हाँ सर.
ये कैंसिल हो गया एंड देन mr
सब्ट्रैक्ट क्यों किया तूने? दोनों सेम सेंस, दोनों सेम सेंस में मूव कर रहा है ना. फाइनली both will be moving together.
Excuse me, sir.
हाँ बोल शिव.
So in this case, the particles, the axis is through the center of mass, right?
हाँ हाँ.
Okay. So is that by default, or like in a question, if it says it's rotating about its axis, by default, is it through the center of mass?
Yeah. So its axis means the center of mass.
Okay.
Disk का axis is geometrically the one passing through its center.
Through the center of mass and perpendicular to the plane.
हाँ.
Okay.
Okay. And loss in KE. So loss in KE is basically initial kinetic energy minus the final kinetic energy, right? Initial kinetic energy का हमने फॉर्मूला देखा है, half ICM omega square. Okay, the formula is half ICM omega square plus.
So I didn't understand why would they have the same angular velocity after like.
So why does velocity even change? क्या है ये question में? Why can't they have different velocities? Why does anything need to change in this question?
Because of friction
between these two, right? So friction का मकसद क्या है? Why is friction acting? It does not like the fact that these two surfaces are sliding on each other.
Got it, yeah.
So friction will eliminate that.
Got it. It it will reduce the friction. It will reduce
So
the.
it will reduce the slipping. So finally, there will be no relative slipping between them. ठीक है? अच्छा, kinetic energy का formula होता है half ICM omega square plus half m VCM square. ठीक है? And because VCM is 0, because the center of mass is not moving, it's just simply going to be half ICM omega square, right? यहाँ एक stationary axis के लिए formula होता है half I about that axis omega square. ठीक है? तो ये axis है mr square by उसके about mr square by 2. So half mr square by 2 omega square. This is initial kinetic energy. Finally, the kinetic energy is going to be अब total moment of inertia. अब दोनों एक साथ move कर रहे हैं, हाँ? तो दोनों को add करके you can say moment of inertia is 3 mr square by 2. 3 mr square by 2. दोनों एक साथ move कर रहे हैं. And omega is omega by 3. Right? So that's your final kinetic energy. When you subtract them,
So VCM is not given.
VCM is 0. ये हिल नहीं रहा है, just rotating about its axis. उन्होंने नहीं बताया कि axis भी हिल रहा है. It's just rotating about its axis. Okay? क्या आएगा? तो ये आ जाएगा mr square omega square. This is 1 by 4 and that is 1 by 12. 1 by 4. उधर ऊपर 3 नीचे 9 minus 1 by 12. So the entire thing becomes one by 6. Mass square omega square by 6. ठीक है? Shiv, I think did you do this? इसका moment of inertia mr square लिया था क्या तूने?
Yes, sir.
ठीक है, मैंने भी शायद किया. That's why I said yes to yours.
So KI is just for the first disk.
नहीं, ये कौन सा K? हाँ, KI is just for the first disk because the second disk is not rotating. Second disk is perfectly still at first. Okay, eventually they start rotating. Cool. All done with this page.
And what's KF?
KF is so the final state. I didn't want to draw it. Final state is when they are both rotating with an angular velocity of omega, right? So finally, m भी rotate कर रहा है, 2m भी rotate कर रहा है.
No, like what did you equate here?
The question was find the loss in kinetic energy.
Yeah.
Loss मतलब initial kinetic energy minus final kinetic energy. Final kinetic energy लिख रहे हैं.
Final kinetic energy minus initial.
वो तो change हो जाएगा. Loss पूछ रहा हूँ, loss. Final minus initial करेगा तो कुछ negative answer आएगा. कितना negative? What is कितने से कम हो रहा है? The loss is always initial minus final. ठीक है, yes. यहाँ पे ठीक है. Final moment of inertia 3 by 2 mr square साथ में move कर रहा है. Final omega by 3 हो गया.
तो subtract क्यों किया?
Initial minus final बताएगा ना कितने से कम हुआ. मेरे पास आज 100 रुपीस है, कल 80 रुपीस है पॉकेट में, तो आई हैव लॉस्ट हाउ मच? इनिशियल माइनस फाइनल.
नहीं, वो मतलब RHS और LHS में आपने क्या लिखा? Like what's the relation between them? So
ये इसकी बात कर रहा है.
ये टर्म क्या है?
ये मैं तुम्हें फॉर्मूला दे रहा हूँ.
अच्छा.
इन केस यू डिडंट नो, काइनेटिक एनर्जी का ये फॉर्मूला है. वो टर्म नहीं है, हाफ एम VCM स्क्वायर टर्म नहीं है, तो सिर्फ हाफ आई अबाउट द सेंटर. ओके, एक और एग्जांपल करते हैं. लेट्स से दिस इज so let's say this is a merry-go-round. और लेट्स से ये merry-go-round का मास है लेट्स से इसका मास है 40 kg, 40 kg, ठीक है। और लेट्स से इसका रेडियस है, मैरी गो राउंड का रेडियस है 2 मीटर, ओके। अब यहाँ पे लेट्स से एक बच्चा खड़ा है, ठीक है। बच्चे का वेट है 50 kg। टॉप व्यू है इसलिए थोड़ा छोटा दिख रहा है, बट ऊपर से देख रहे टॉप व्यू है। बच्चे का वेट है 50 kg and he is standing at a distance of 1 meter. Okay. All right. What else? यहाँ पे बच्चे का दोस्त है जो एक बॉल फेंकता है बच्चे की तरफ, ठीक है। तो दैट बॉल का मास इज so there's a merry-go-round 40 kg का जिसका रेडियस इज 2 meters, ठीक है। दिस इज द टॉप व्यू। merry-go-round is going to rotate about its axis, ठीक है। That there's a kid over there जिसका weight है 50 kg. There's his friend over here who's going to throw a ball to him, ठीक है। So he's throwing a ball to him like this, and वो ball का mass है, this is a ball, ball का mass है 10 kg, 10 kg, okay, that's it. And ball का velocity, like by the time it's reaching his hand, the ball का velocity is let's just say it is 5 meters per second, okay, 5 meters per second. So this is the scene. 50 kg का boy है, 10 kg का ball है, ball horizontally boy की तरफ जा रहा है, the boy catches the ball, ठीक है, the boy catches the ball, the merry-go-round was at rest initially, so this is at rest initially, ठीक है। फिर उसके दोस्त ने उसको बॉल दिया, ये बॉय भी एट रेस्ट इनिशियली, ठीक है। द बॉय कैचेस द बॉल, उसके बाद क्या होगा, द merry-go-round starts rotating, ठीक है, पीछे की तरफ, starts rotating in the anti-clockwise sense. With an angular velocity omega. So I want you to find omega. You're going to assume that there is no assume that there's no friction between the axle of the merry-go-round and the merry-go-round itself. तो वहां से कोई torque नहीं आएगा. There's no friction over there.
Initially, the merry-go-round wasn't rotating.
Initially, it wasn't rotating. अरे simple यार. सोच तू उधर खड़ा है, merry-go-round सब rest पे, it is free to rotate. ठीक है? And somebody throws a ball to you. So when you catch the ball, don't you think यार, as you catch the ball, फिर ये पूरा इसको पकड़ने के बाद ये अब ऐसा घूमेगा. हाँ, कितने से घूमे, कितने?
फ्रिक्शन के चलते घूमेगा. Friction it will rotate, right?
There's friction between the boy and the platform. Boy platform पे हिल नहीं रहा है, फिसल नहीं रहा है, but everywhere else there is no friction. Okay, so can you find the final omega? Okay, so find omega. So there's no friction between the ground and the merry-go-round no friction between the axle
The distance between the ball and the axle is 1 meter. Axle is like the center point.
हाँ axle जिसके ऊपर वो घूमता है वो rod.
Oh, axle is it the center of mass also?
Yes, for the merry-go-round.
Got it.
So no friction between the axle of the merry-go-round and the merry-go-round. A bit lamba sentence. I'll just make this from. No friction from. Boy is always at rest with respect to the merry-go-round. ये मेरी गो राउंड को मैं शॉर्ट में MGR लिख रहा हूँ, ठीक है. Have you understood the concept, na? क्या?
Should we apply conservation of angular momentum?
About which axis?
Because initially it was at rest, right?
हाँ.
So
And let's just discuss like what's happening. यहाँ पे क्या लगा सकते हैं? Conservation of angular momentum, conservation of linear momentum लगा सकते हैं क्या? Can we apply conservation of linear momentum? So conservation of linear momentum can be applied if force is 0. Now obviously there is going to be some rod over here. Okay, this is the axle of the merry-go-round. So there's going to be some rod over here holding the merry-go-round in its place. So you cannot apply conservation of linear momentum because that rod is going to apply a force on the merry-go-round. Right? कुछ तो force लगाएगा, इसके कारण कुछ तो force आएगा. We don't know what that force is, but उस force के कारण you can't apply conservation of linear momentum. Can you apply conservation of angular momentum? And if yes, about which axis?
So about the axle.
About the axle. क्योंकि सिर्फ इस axle के about वो force का torque 0 होगा.
So linear momentum के axis define करना is not necessary, right?
Of course, yeah, linear momentum में axis का सवाल ही नहीं था ना. F external is dp by dt.
Yeah.
तो F external जब तक है, you cannot conserve linear momentum. ठीक है? ये force के कारण axle जो भी force लगाएगा, you don't know its direction. मैंने randomly draw किया है, उसके कारण you can't conserve linear momentum. But इस force के ये force के कारण अब torque आएगा तो you can't even conserve angular momentum. But then now can we pick an axis जिसके about इसका torque 0 होगा? The answer is yes. We can pick this axis itself because this force is from the axle. It's going to pass through this axis.
Because the distance, like
are perpendicular zeros. If you, ठीक है? So if a force intersects an axis, उसके कारण torque is 0.
so
Simple.
We can apply conservation.
So you can apply conservation of angular momentum about this axis alone. Okay, so proceed with that. I'll write out what I said in words, but you guys proceed with solving. See what is in. अब पता है तुम्हें. Just try to solve it.
Initially the angular momentum was 0, right? So
ये बॉल है ना, तुम देखो किसको सिस्टम में लोगे, बॉल
इनिशियली तो बॉल नहीं था यार।
अगर बॉल को सिस्टम में नहीं लोगे तो बॉल के कारण एक टॉर्क लगेगा बंदे के हाथ पे, यू वांट टू अवॉइड दैट, बॉल को भी सिस्टम में ले लो. So okay, now just try to solve. This is my advice. I've explained what is going on. You can conserve angular momentum about this axis. किस system के लिए? Platform plus boy plus the ball. ठीक है? और पहले प्लेटफॉर्म और बॉय का एंगुलर मोमेंटम नहीं है, सिर्फ बॉल का है. और बाद में सभी एक साथ मूव कर रहे हैं. प्लेटफॉर्म घूम रहा है, बॉय प्लेटफॉर्म के साथ साथ घूम रहा है, बॉल बॉय के हाथ में है तो बॉल भी प्लेटफॉर्म के साथ साथ घूम रहा है.
एंगुलर मोमेंटम थोड़ी वो तो लाइक लीनियर मोमेंटम है ना, बिकॉज़ इट्स
R cross P, linear momentum times perpendicular distance. Okay? Strike a look, come on. जो हो जाता है R into P, perpendicular distance into P.
so तो फाइनली बॉल का वेलोसिटी विल बी 0, राइट?
नहीं ना, बॉल विल बी इन द बॉयज हैंड. तो जब प्लेटफॉर्म घूम रहा है ओमेगा से, बॉल भी घूम रहा है, बॉय भी घूम रहा है, सभी एक साथ घूम रहे
तो उसमें बॉल 5 मीटर पर सेकंड वेलोसिटी से फेंका है ना.
हैं. हाँ, वैसे मानो बंदे का हाथ पे जब पहुंचता है तभी भी वेलोसिटी ऐसा 5 मीटर्स पर सेकंड है.
तो बॉय का एंड बॉय का आईसीएम क्या है?
आई तो these are, come on, these are most basic moment of inertia. ये तो
अच्छा हाँ,
छोटा है तो m
अच्छा हाँ, वो
r
उसके
square,
लिए
m r square होगा. And it should be clear why we are taking these systems now. So we're taking the ball plus the boy plus the merry-go-round because वरना सबके बीच में कुछ तो internal force है. We don't want to work with. Ball और boy के बीच में internal force रहेगा. When the boy is catching the ball, boy and platform के बीच में एक friction होगा. Right? That's how the boy does not slide on the platform. So we don't want to worry about those things.
Omega is equal to 5/18.
I'll check. I mean, no, check up. But idea, I hope clear है. क्यों system ऐसा ले रहा है ना? And system ऐसा लेने के बाद क्यों हम ये axis ले रहे हैं? So our axis is the axle itself, the rod holding that thing in place, or the center of mass of the basically of the merry-go-round. That is our axis. And because torque external उसके about 0 है, Q 0 है, वो भी समझ लो है ना? Ground से कुछ friction नहीं लग रहा है. Axis का force is passing to the axis. और ये सारे बाकी वाले torques internal हो गए. Boy और platform के बीच में, boy और ball के बीच में. Right? So therefore torque external is 0. Therefore above this axis, initial and final angular momentum will be conserved. Now,
Is this a hollow circle or?
merry-go-round, यार, इधर खड्डा नहीं हो सकता ना? He has to stand on it. It's a disc. ठीक है? It's a disc. So let's just see the working. So initial angular momentum will be boy का plus ball का plus merry-go-round का. This should be equal to the final angular momentum. You of course don't need to write like this. मैं explain कर रहा हूँ इसलिए I'm writing in this much detail. अच्छा, अब boy का initial angular momentum was 0 क्योंकि घूम नहीं रहा है. Ball का initial angular momentum क्या आएगा?
50.
Very nice. So R perpendicular, that's 1 meter. It should have been clear. R perpendicular into ball ka mass 10 into velocity. Perfect. 50. Okay. So ball ka aa jayega 50. So we'll just say R perpendicular into MV. Right. So R was 1 and mass was 10 and velocity was 5. ये वहां से 50 आ रहा है और merry-go-round का इनिशियली कुछ नहीं था. फिर boy, ball and merry-go-round का final angular momentum about the axis. Now bear in mind that axis is the IOR, so you can directly use the formula I omega axis के about. ठीक है? तो I omega लिखते वक्त तुम सब चाहिए तो सबका I combine भी कर सकते हो. You want, you can combine everyone's moment of inertia. So let's say you can combine moment of inertia of the ball plus moment of inertia of the boy plus moment of inertia of the merry-go-round. You can club all of them and say angular momentum is total I omega. Sabka omega same hone wala hai. They're all going to rotate with the same angular velocity. In fact, ये clockwise sense में था, तो ये omega भी, sorry, anti-clockwise में था, ये भी anti-clockwise sense में होगा. ठीक है? या तो वैसा लिख सकते थे या बॉय एंड बॉल के लिए mv into r लिख सकते थे. वहां पे v होगा r ओमेगा, तो एक ही चीज होगा mr square into omega या mvr into omega and v being r omega gives the same thing. ठीक है? So you could write it either way. Anyways, तो यहाँ पे आएगा 50 is equal to moment of inertia of the ball. It's like a point particle, so we'll use mr square. So that'll be 10 into 1 का square. moment of inertia of the boy, वो भी platform मैंने है ना बड़ा draw किया है. I'm not giving you the size of the boy. Fair to assume the boy is also in that sense like a point particle, है ना? उसका mass vertically फैला हुआ है, ऐसा horizontally फैला हुआ नहीं है. तो mr square की तरह ले सकते हो. Boy का mass was I think 50, okay. And distance from the axis was 1. And similarly, moment of inertia of the merry-go-round. Now, this is a disc. So the formula is mr square by 2. So merry-go-round ka mass was 40, radius was 2.
Mass was 60, right?
नहीं 40 था
40.
अच्छा, 40 है, 60 है.
ठीक है, my unclear था क्या?
Oh, हाँ,
40. ठीक. Anyways, 40 r square by 2, and then all of that into omega. Great. Yeah, I mean, of course, you can solve that. But ये किया तुम लोग ने समझ में आया ये?
yes, मैं 40.
हाँ, that's fine. So yeah, anyways, 10 plus 50 plus, I think that will be 80. Okay. Come on. So 140 omega is 50 by 140. Clockwise direction.
Clockwise,
Anti-clockwise direction में. क्यों? क्योंकि इनिशियली भी एंटी क्लॉकवाइज था. वो जो बॉल फेंका, बॉल का एक एंटी क्लॉकवाइज एंगुलर मोमेंटम था ना, तो फाइनल सिस्टम का भी एंटी क्लॉकवाइज होगा. क्या हो गया है आज? कहाँ से आता है तू?
Malad.
ठीक. हाँ. You can take a short break, like while this guy settles in. वॉशरूम एक फ्लोर ऊपर है,
नहीं यार
थर्ड पे भी है. All clear, Shiv, Vikrant, Vishal. Okay. You guys have one more lecture today? नहीं. उसे नहीं हो गया.
Aryaditya.
Arya, sorry,
Aryaditya.
Aryaditya.
So,
We had a look at conservation of angular momentum.
okay.
कुछ पता है उसके बारे में?
I guess if a torque isn't applied, then angular momentum is conserved.
If a torque is not applied.
हाँ.
Torque is dl by dt.
Yeah.
And if torque is 0, angular momentum is conserved.
So that's it.
Some examples later.
So what happened was halfway through, I forgot my wallet, so I actually back and
Oh.
I should have attended online.
You could have joined. So एक छोटा सा break दिया मैंने, even for those online you just want to freshen up, you can just do that. मेरे को just बता देता हूँ, like ये क्वेश्चन किया था इसमें ये
So if,
हाँ
if torque is zero, then could this happen that linear momentum is converted into angular momentum or vice versa?
if torque is zero, angular momentum is conserved. It won't increase, it won't decrease. तो बोला linear is converted to angular, it won't increase. जितना है angular momentum होगा. And ये भी समझो, these are two independent concepts. If F external is zero, linear momentum is conserved. वो एक अलग कहानी है. If torque external is zero, angular momentum is conserved. These are two independent things that are going on. और यहाँ पे we just wait for the other guy also to come. यहाँ पे जैसे एक example दिया था कि this was the platform. ठीक है, this platform was free to rotate about the axle. और मैं बोला कि axle is frictionless, so the axle does not provide any resistance to the rotation of this platform. The floor this platform is on, that is also frictionless. I said there was a boy standing on the platform. Boy और platform के बीच में friction है, so that the boy can stay at rest with respect to the platform. यहाँ पे the boy's friend throws a ball towards the boy, which he catches, and this is the velocity of the ball before the boy catches it, and everything. These two were initially at rest. So just to go over the concept was कि because there's because there's this force, we can't conserve linear momentum. There is a force holding the axle in place, right? तो पूरा चीज को system लोगे तो you can't conserve linear momentum, but you can conserve angular momentum about that axle. Because the force is passing through the axle, it will have no torque about the axle. So that's the scene. जो initial angular momentum है, वो axle और boy का नहीं है, इस ball का है. And बाद में when the boy catches the ball, वो combined system का angular momentum हो जाता है.
So can you tell the relation between alpha and angular momentum?
Alpha वैसा direct नहीं है. Alpha is, so angular momentum is I omega. So the way omega relates to alpha, वैसा angular momentum relates to alpha. Alpha relates to torque. So if you ever want instantaneous alpha, you will have to just see what is the current torque. Okay, all right. Okay, so we'll move on now to a very interesting application of conservation of angular momentum, and in fact it's an application of what we have done in the previous chapter as well. So this will be an application of quotient of restitution and an application of conservation of linear momentum. All right, so this is a topic called as angular collisions.
So can you give a brief summary on quotient of restitution?
इसमें देखेंगे ना, velocity of separation by velocity of approach. We'll थोड़ा इसमें देखेंगे. So angular collisions is what? When will be questions where imagine there's a rod like this, one ball comes and hits the rod. After the ball, it may be an inelastic collision, it may be an elastic collision, something in between. Ball rod को hit करने के बाद ball का क्या velocity होता है, या rod का center of mass का क्या velocity होता है, या rod का क्या omega होता है. These are all questions that could be asked. Okay, so that's what we're basically going to see in angular collisions. ठीक है, how objects, पहले collision क्या था? Earlier collision only dealt with velocities. There were particles colliding. Now we have extended objects colliding, and when extended objects collide, their center of masses can get some velocity, centers of mass can get velocities, and they can also have an omega. Okay, so that's what this is about. Interesting. Eh? We'll start with the first case where we are considering collision with a hinged rod. Okay, so hinged rod on a smooth table. ठीक है, imagine a hinged rod on a horizontal smooth table. इनफैक्ट बाद में बताऊंगा कि यार ग्रेविटी के कारण भी फर्क नहीं पड़ेगा, because you might have learnt in collision कि gravitational forces are, have you heard the word non-impulsive? Anyone?
Yes, sir.
है ना? So non-impulsive का मतलब क्या होता है?
So when a force acts for a very short period of time but changes momentum significantly.
That is impulsive. The non-impulsive
So non-impulsive is opposite.
is the opposite of that. Very nice. So अभी मैं जो example दूंगा, I'm just considering this kind of collision between a rod and a particle, and we are just assuming it's taking place on a smooth horizontal table. But later I'll just mention this point कि अगर gravity भी होगा, कुछ फर्क नहीं पड़ेगा to the scene just before and just after collision, क्योंकि gravity non-impulsive होता है. It doesn't suddenly change things. Takes time to change things. रॉड उठेगा तब उसका थोड़ा है ना, उठते उठते ओमेगा कम होगा, बट वो स्प्लिट सेकंड जिसमें कोलिजन्स होता है, इन दैट स्प्लिट सेकंड ग्रेविटी इज नॉट बिग इनफ टू चेंज थिंग्स. द फोर्सेस इन्वॉल्व्ड, द नॉर्मल फोर्सेस इन्वॉल्व्ड, दे आर बिग इनफ टू सडनली चेंज थिंग्स. So this is, so इसमें क्या है ना, what I'm trying to say is even if gravity is present, okay, so the scene just before collision, ठीक है, just before collision, मान लो this has some velocity, मान लो that has, you know, who knows, that may have some omega. But just after collision, this guy may have some new velocity, and that guy may have some new omega. ठीक है, just after collision. But just before and just after collision के दौरान, I mean, sorry, between the instances just before and just after collision, gravitational force जो है ना, ये बहुत ही छोटा सा टाइम फ्रेम है. उस छोटे से टाइम फ्रेम में अगर ग्रेविटी भी होगा, if this was a vertical diagram, अगर ग्रेविटी भी होगा तो भी ग्रेविटी ज्यादा कुछ कर नहीं पाएगा. ठीक है, that's what we call as, categorize as non-impulsive forces, because these forces, gravity क्या mg है ना, so these forces take time to change the velocity. These forces are finite, they take time. From time दो rod उठना start करेगा, तो in that large time frame you can see कि अच्छा इसका ओमेगा कम होते जाएगा. But just before and just after collision के दौरान gravity is as good as not there, which is why even if you have particles colliding in the air, you don't sit and worry about gravity. You apply your सादा collision वाले equations. And that's the idea. These forces, यहाँ पे contact के वक्त जो normal force होगा,
T is very small, right?
T is very small. But ये contact के वक्त जो normal force होगा, that is what we call as impulsive. That is very large, and that is significant to suddenly change the momentum of the system. Okay. All right. Okay. So in this case, let's see what are the equations involved. So if you have a hinged rod, these will be the equations involved. I'll walk you through the equations and then I'll give you a question that you can try and solve. So two equations will be involved. Very similar to what we just did with the merry-go-round. अगर एक hinged rod है, तो hinged rod मान लो कहीं ना कहीं hinged है ना, तो hinged rod के कारण, वो hinge के कारण force आएगा, कुछ तो force लगेगा collision के दौरान, and that force is going to react to whatever collision is taking place, right? So that force is going to be impulsive. तो तुम momentum, linear momentum conserve नहीं कर सकते सिस्टम का, बट वो हिंज रिएक्शन के कारण के बावजूद तुम इसके अबाउट टॉर्क कंजर्व, सॉरी, एंगुलर मोमेंटम कंजर्व कर सकते हो. व्हाई? टॉर्क अबाउट द हिंज इज गोना बी जीरो, राइट? हिंज का कोई तो रिएक्शन होगा, अननोन हिंज रिएक्शन रहेगा, ठीक है, देयर विल बी सम हिंज रिएक्शन, एंड दैट हिंज रिएक्शन विल नॉट अलाउ यू टू कंजर्व लीनियर मोमेंटम, बिकॉज़ देयर इज एन एक्सटर्नल फोर्स, बिग फोर्स, but you can conserve angular momentum. So we can say torque about the hinge is zero. Why? Because the force is passing through the hinge. So वो force का torque hinge के about zero होगा, ठीक है. So torque about the hinge is 0, जिसके कारण angular momentum about the hinge is going to be conserved. So that is one equation. अपना merry-go-round सवाल की तरह ही है. तो L initial is equal to L final. Angular momentum about hinge is conserved. समझा? ये एक इक्वेशन हो गया.
So during the collision,
Hmm.
the linear momentum of the object will change. Right?
Yeah, it could change. During the collision, linear momentum could change because of this guy. Because there is a large thing, this is going to be impulsive. So there is an external impulsive force.
I'm not talking about the hinge to one.
हाँ.
Other particles.
अरे वो तो होएगा ही ना, ये तो उसको मार रहा है ना.
हाँ, उसका तो
ऑफ कोर्स होगा.
और उसका वो भी चेंज होगा.
किसका?
Angular.
हाँ, वो तो उसके अबाउट भी हाँ चेंज होगा ना. See, ये तो यार if you're going to sit and take one of them individually as the system, उनका तो सब कुछ चेंज हो रहा है. There is an external force acting on them, right? Now all these collision questions तो एक को system में लेके कुछ होने नहीं वाला है. You will always tend to take both in your system so that you don't have to worry about that internal force. ठीक है? Now even if we take both as a system, because of this guy we cannot conserve linear momentum. This is some unknown hinge reaction. So to avoid that, we will take our torque about the hinge and we'll say how that we'll show ki acha torque about the hinge is 0, and then that allows us to conserve
So
the angular momentum.
Not sure about the hinges का ये reaction. मतलब linear frequency के बारे में we're not sure. And so
We don't know its direction. We don't know its magnitude. Huh?
And so I'm guessing if it's an elastic collision, then energy is conserved.
Huh. So good point. I'll come to that point. The L above the hinge is conserved. Now the second equation. The second equation is he's saying ki if the collision is elastic, we'll conserve energy. That's true. If collision is elastic, energy is conserved. Let me just talk about collision between two blocks. Previous chapter wala collision. Usme bhi I've seen a lot of students, jab elastic collision hota hai, I've seen a lot of students try to apply energy conservation ka equation. Why? It's valid. But I don't think you guys have then understood where quotient of restitution comes into the picture. जो सादा collision है, अगर collision elastic भी है ना? कितने unknown होता है? Final 2 velocity unknown होता है. 2 velocity के लिए 2 equation चाहिए होता है. एक equation सब लिखते हैं momentum conservation. And I have seen students try to apply energy conservation. है ना? Initial kinetic energy is final kinetic energy. They have tried to apply energy conservation as the second equation. It's not wrong. It is correct. But what is the problem? That kinetic energy wala equation is going to be in terms of v square. It's not a linear equation. Momentum to v hoga, v1 v2 hoga. Kinetic energy mein v1 square v2 square hoga. That's not a good equation to work with. So if you have seen how quotient of restitution was derived, तो energy conservation वाला equation लोगों ने लिखा था half m v1 square v2 square वाला energy conservation वाला equation, and then they solved these two simultaneously and proved for elastic collisions velocity of approach is velocity of separation.
But we'll have to.
सुन एक मिनट सुन पहले. ठीक है, तो एनर्जी कंजर्वेशन और मोमेंटम कंजर्वेशन को साइमल्टेनियसली सॉल्व करके प्रूव होता है कि वेलोसिटी ऑफ सेपरेशन इज वेलोसिटी ऑफ अप्रोच. सो दिस इज
given by
हाँ, which is from here we defined कि in this condition we'll say we define D and then said E is equal to 1. तो इसका मतलब ये ध्यान से सुन लो, whenever you have, of course when you have non-elastic collision तो ये तो valid भी नहीं होता है, and when you have elastic collision तभी भी don't waste your time with this equation.
Okay.
उसी से आता है velocity of separation is velocity of approach. ठीक है?
Okay.
So never in collision, during the collision will you ever have to apply energy conservation. It is valid for an elastic collision, but you won't have to apply it.
We can still solve it, but it will take time, right?
It will take time. It will be a big waste of time. Advanced में there'll be more things जो करना पड़ेगा उस time frame में. अच्छा, so the second equation in general will be quotient of restitution. Okay, so E is velocity of separation upon velocity of approach. अब ये I have to stress कि यार velocity of separation ये समझ में आता है ना, velocity of separation मतलब कितना तेजी से दूर जा रहा है, velocity of approach कितना तेजी से पास आ रहा है. But ये किस points के लिए defined है? Is it defined for the, now we are dealing with extended bodies,
So
different
point of contact.
points. Very nice, Shiv. So different points move with different velocities. Okay? So please understand and remember that this equation does not talk about the center of mass. This equation is defined for the points of contact. So here the velocities involved are the velocities of the colliding points. ठीक है, जो भी यहाँ पे इस इक्वेशन में जो भी velocities लेंगे, there will be velocities of the colliding points. ठीक है, points of contact, not the centers of mass, and not the velocities of the center of mass. Centers of mass. Okay. That's it. So two equations.
So what about conservation of momentum? Conservation of momentum.
हाँ, I already mentioned it. What is the answer? मैंने already बताया.
Momentum is not
Takes too much time.
Sorry?
So it takes too much time.
नहीं वो energy conservation takes too much time. Linear momentum तुम कर ही नहीं सकते इस बंदे के कारण.
Hinge applies, of course.
Hinge reaction के कारण you cannot conserve linear momentum. There is an external force. So in questions में you cannot conserve linear momentum. ठीक है, तो conservation of linear momentum.
Oh yeah, I was talking about angular momentum. That we can conserve.
अरे वो पहला point है.
अच्छा वो LI
ठीक है, conservation of linear momentum cannot be applied due to the hinge reaction. Very important to know what is available, what can be done, what cannot be done. तो इसमें ना this case that we are starting with, this is a good case. इसमें दो ही unknown रहेंगे, दो ही unknown रहेंगे, ज्यादा से ज्यादा दो ही equation रहेगा. दो unknown क्यों? एक इसका कहानी after collision क्या है, इसका velocity, और एक वो rod का ओमेगा क्या है. Just two unknowns. Okay, I'll give you a question. उसमें भी easier is if the collision is inelastic, then there's only one unknown. Inelastic collision में साथ में move करेंगे. That's the easiest case.
So V separation and V approach is relative velocity.
Yes, V separation and V approach is the relative velocity of these 2 points. Okay, ये जो दो ये point और ये point के बीच में इनके लिए तुम V separation and V approach define करोगे. Okay, so V separation and V approach are the relative velocities of these 2 points before collision and after collision. Okay, चलो एक question करते हैं.
Relative velocity with respect to
Relative velocity by default means of one guy with respect to the other. हर frame में same होता है relative velocity. It means you already sit on one of their frames. Okay. See, so we'll start with the easiest case and slowly we'll increase the complexity. Okay. Let me know when you're done. So case one may be like the first type, two types hai. The first and the easiest type will be when the collision is inelastic. एक ही unknown रहेगा इसमें, ठीक है? बहुत easy. तो inelastic collision, imagine I have a rod, ऐसा, ठीक है? And rod का mass है m. Okay, rod, uniform rod का mass है m. Brackets में m और l लिखता हूँ, that means I mean the mass is m, length is l. और rod पे एक 2m mass का particle हमने फेंका है, उसका velocity है v, and that particle is headed for a point which is l/2 distance below the hinge. Okay, and it's given कि the collision is inelastic. So given that the collision is inelastic, find the final omega of the rod.
So do we also have oblique collisions in rotation?
हो सकता है, but you have understood, if you've understood oblique collision over there, so you would have understood कि oblique, तो oblique में यार ये वाला जो along the rod velocity है वो कुछ करता नहीं है, वो intact रहता है. It's only the along the normal velocity, head-on velocity, which actually collides.
The 2m and the m, like the m is same, right? Or
हाँ,
are they different?
of course the same m. Capital M, capital 2m.
Okay, I got it, yeah.
You missed the fact that this guy will also rotate, no? This is stuck to the ground.
What's the axis we're taking?
Look at point 1.
So hinge is like this or like this? Like इसके अंदर है hinge or it's like this?
नहीं अंदर मतलब ऐसा through the rod.
Yeah.
तो फिर वो कुछ फिर तो घूमेगा ही नहीं ना.
Yeah.
Hinge बेसिक अभी ऐसे डायग्राम में hinge means it's
Yes, sir.
ये इसके perpendicular है
Got it.
और rod ऐसा rotate कर सकता है. The changes.
And this process.
अच्छा.
So what's the angular speed of 2m? Because I omega.
You given तो और formulas है ना. अबे इसको I omega नहीं तो R cross.
तो r l/2 है यहाँ पे क्या?
हाँ, perpendicular distance into MV.
अच्छा हाँ, yes, I think that.
अच्छा वो काट के सही गुड एक इक्वेशन एक लाइन मतलब एक इक्वेशन में आंसर आएगा सिर्फ एक ही अननोन है
So we are assuming E is 1, right?
inelastic चिटक रहा है E is 0 साथ में that's why I said there's only one unknown because the final scene is this they're going to move together बाकी टाइप के कोलिशन में दो अननोन रहेगा बिकॉज बॉल का भी वेलोसिटी अननोन रहेगा ना बाद में
So they'll have same velocities after collision.
you're basically you're moving together this is the final scene they're all moving with omega ऑनलाइन किसी का आ रहा है आंसर नहीं बता दो just stress key in this there's only one unknown right and that one unknown is omega so you need only one equation you don't need the second one because E is itself 0 right all the second equation सिर्फ इतना बताएगा कि ये चिटक रहा है V separation is 0 you anyways understand कि चिटक रहा है so only one equation needed and that's going to be the first one
So the perpendicular distance will be constant, right? Like final angular momentum के लिए 2m का perpendicular distance will still be L by 2.
हाँ because
Or would it be
यहाँ पे चिटक गया ना where else will it go
अच्छा हाँ yes.
axis से distance
0 to yes.
okay so one equation needed so we will say L about the axis what is my axis this guy the hinge so L about the hinge initially is L about the hinge finally
Or it will be mn square by 3.
so but what is my system is both of them ठीक है दोनों सिस्टम है इनफैक्ट इसमें ये L rod
ml square by 3 plus ml divided by 2.
ठीक so L rod plus L ball initially just bear in mind L rod plus L ball finally दोनों सिस्टम में you're right ठीक है तो रॉड का इनिशियल एंगुलर मोमेंटम वो 0 ठीक है बॉल का इनिशियल एंगुलर मोमेंटम ये पार्टिकल जैसा है so mvr is the formula mv perpendicular distance so 2mv L by 2 2m into v into L by 2 every conservation of angular momentum equation या every angular momentum equation in general keep track of the directions clockwise anti-clockwise just keep track of that this is anti-clockwise
So it should be v by 2 by L, right? V by L by 2 because it's like
formula है mv r perpendicular r cross mv into r perpendicular force torque is force into lever arm यहाँ पे force की जगह बस क्या है momentum into lever arm momentum is 2mv perpendicular distance is L by 2 उनका product है
I used I into omega. And I would be 2m into L by 2.
हाँ I will be 2m into L by 2 whole square omega will be v by L by 2 comes to the same thing ठीक I for a particle mr square and v is omega is v by r so that again gives you mv into r perpendicular अच्छा, सो ये एल बॉल इनिशियल हो गया, एल आर फाइनल। तो इनको तुम क्लब कर सकते हो बिकॉज यू कैन से, या क्लब नहीं भी करना ठीक है। रॉड का फाइनल एंगुलर मोमेंटम विल बी एम एल स्क्वायर बाई 3, इधर कर ले आई ओमेगा, एम एल स्क्वायर बाई 3 ओमेगा, ठीक है। और बॉल का भी फाइनल एंगुलर मोमेंटम यू कैन से, अच्छा बॉल का मोमेंट ऑफ इनर्शिया विल बी एम इंटू ये डिस्टेंस स्क्वायर बाई 2, सॉरी एम इंटू ये डिस्टेंस स्क्वायर, है ना, एम आर स्क्वायर। उसका मास है 2m और उसका डिस्टेंस है l बाई 2 का स्क्वायर। ये आ गया अपना इक्वेशन। 2m v l by 2 is ml square by 3 omega plus 2m l by 2 whole square omega. Got it? Which gives us mbl is equal to ml square by 3 plus
ml square by 2.
ml square, हाँ, which is
Angular momentum for me it's coming ml by 2 उसका the back to m का, shouldn't it be ml by 2
क्या लगाया तूने, क्या लगा रहा है वो बता।
using I omega.
तो what is I? Mass is 2m, distance is l by 2,
2m into l by 2 plus square.
हाँ, तो आ जाएगा m l square by 2.
Now I'm talking about the RHS. RHS में 2m
2m l by 2 का whole square into omega. What is omega? Collision के बाद what is omega? V by r,
अच्छा
V by l by 2. Okay, तो ये आ जाएगा ml square 1 by 3 plus 1 by 2.
calculation.
ये 5 by 6, तो omega is mm काट दो, ll काट दो, omega is 6v by 5l. Okay. All clear online?
Yes, sir.
तो यार एक लेवल बढ़ा देता है। I'm going to keep most of it the same so that, but just I want you to try this question again. If E was half, if E is 1 by 2, same question try karo. This time you will try to find omega of the rod. But this time you'll encounter two unknowns. Iska velocity will be an unknown after collision, and omega of the rod will be an unknown. So you'll have to use both equations. First one जो ये ऐसा है, and the second one as well. Just try कर लो. The question is, so इसका question is solve the previous question if E is half. Put it on this page and I'll come back to it. Solve the previous question for E equal to 1 by 2. It's no longer an inelastic collision. So, and this gives us type B. Type B is cases which are not an inelastic collision. You'll have to use two equations, yes. Because this time the particle is not sticking to the rod, which means particle का भी velocity collision के बाद unknown होगा. तो दो unknown है. तो मैंने जो starting में जो दो equation दिया था, तुम्हें दोनों use करना है. Try कर लो यार.
Quotient of restitution will always be given.
हाँ, of course, हाँ, I mean देंगे. Inelastic या elastic ऐसा बोला नहीं है, तो देंगे.
For the second one, we have to find out what omega of what.
The rod. Same
Omega.
question. Yeah.
I got it. I got this from the last question. So initial would be the same.
Initial is MBL. What's yeah, sir. Velocity separation is and velocity approach. Approach V था ये V by 2 है. Velocity rod minus particle. हाँ बोल.
यहाँ पे LHS में यहाँ पे ओमेगा 1 ओमेगा 2 type A but type B के omega 1 for example and omega 2.
हाँ.
So will that be the velocity of separation and velocity of
Yeah, omega not directly ना but देख एक दो चीज थोड़ा रिफाइन करा देता हूँ. V will तो इसका velocity will be r omega of the rod, ठीक है? And for the particle I'm telling you to be flexible with both formulas. इसका ऐसा नहीं कि इसका सिर्फ ओमेगा के टर्म्स में तू L सोच रहा है. It'll help. I omega है, MBR भी है, MB perpendicular R भी है.
ये relative velocity के साथ है. It's omega into r होता है.
कौन सा?
जैसे V of separation divided by V of approach.
हाँ.
So how will we find both?
तो stick with. I'm just saying कि stick with the इसको velocity के terms में equation को लिख लो.
Yeah.
Velocity से फिर rod के केस में velocity से rod का omega लिख लो. Particle का you don't need to talk about its omega. If you want to talk about the angular momentum of the particle, just use that MVR perpendicular. You don't need to think of its omega.
I divide by L by 2 to get omega.
Okay. So velocity rod is velocity of particle plus V by 2. Omega of the you divided by L by 2. हाँ. ठीक है.
I got the relationship between omega rod and omega particle.
ठीक है. अच्छा हाँ ठीक है.
MVR square. MVR. What was the relation MVR?
Which one?
Angular momentum.
हाँ MVR perpendicular. MVR perpendicular. या I omega एक ही बात है. Particle के लिए. So what is your final answer?
9V by 5.
Okay, I'll just confirm that. दिखा दो. So this is the scene before collision. Okay? And before collision, you have particular mass 2m heading towards that with a velocity v. Rod is at rest. Okay? I just repeat, this is a rod of mass m and length l. The scene after collision is सच कि अभी मुझे मेरा रॉड का कोई ओमेगा होगा, ठीक है, रॉड का कोई ओमेगा होगा और पार्टिकल का कोई वेलोसिटी होगा, ठीक है. यू वांट, यू कुड ड्रॉ दिस टुवर्ड्स द राइट, यू वांट, यू कुड ड्रॉ इट टुवर्ड्स द लेफ्ट, इट्स अप टू यू, ठीक है. जस्ट मेक श्योर यू हैव ड्रॉन इट एंड यू.
I got the answer.
क्या है तेरा?
3/4V. तो मतलब उसका the rod का final omega is 3/4V.
डायमेंशंस तो गलत है, बट अभी देख मे बी लेट्स सी, इसका थोड़ा अलग आया था, लेट्स सी, अभी जस्ट क्रॉस चेक देख, ठीक है. सो ये मेरा इनिशियल सीन है. मेक श्योर यू हैव दीस थिंग्स वेल थॉट ऑफ. आई एम whatever variables I have to assume two variables. ये particle का final velocity is an unknown, rod का omega is an unknown. Whatever variables you're assuming, make sure you in a way just at least draw the directions of them, because looking at that you're going to write your equations. Okay, अब देखो, I'm going to start with the second equation. Second equation क्या है? Quotient of restitution वाला है ना. तो quotient of restitution says E is equal to half. E is velocity of separation by velocity of approach. Okay, now velocity of approach साफ साफ दिख रहा है, कितना है इस डायग्राम में?
V.
V, ठीक है. अब velocity of separation, ठीक है, तो velocity of separation when two are separating it will be, है ना, दोनों सेम डायरेक्शन में जा रहे हैं, बट दिस गाय इज द फास्टर वन, तो फास्टर वन माइनस स्लोवर वन. बट ये फास्टर वाले का स्लोवर वाले का वेलोसिटी तो v डैश है, फास्टर वाले का वेलोसिटी इन टर्म्स ऑफ द वेरिएबल्स, परफेक्ट. सो इन टर्म्स ऑफ द वेरिएबल्स इंट्रोड्यूस्ड इट्स गोइंग टू बी ओमेगा l by 2. तो फास्टर वाले का वेलोसिटी माइनस पीछे वाले का वेलोसिटी v डैश, ओमेगा l by 2 इसका वेलोसिटी है, माइनस v dash gives you velocity of separation. ठीक है, ठीक है, पक्का. v dash, अरे यार 4 के स्पीड से गाड़ी जा रहा है, दूसरा पीछे 2 के स्पीड से जा रहा है. 4 minus 2 is the relative velocity. ठीक है, relative velocity. And that's why you have to draw these properly. अगर मैं लेफ्ट की तरफ लेता then this would have been plus v dash.
I understood omega into L by 2 minus V dash.
हाँ, तो draw these things before you know getting down to equations and answer and all that calculations.
Excuse me, sir.
हाँ बोल.
So how do you know that it's not going leftwards after collision?
I don't know. So very nice. So that's the thing. I don't need to break my head over whether this is going to the left or the right. I don't know.
Okay.
If,
Okay, so just assume towards the right and then it'll come negative if towards left.
if it, yes, just assume any direction. If it comes negative, it means it's towards the left. Okay? You can assume towards the right, yeah, assume towards the left. It makes no difference. Just make sure. Just make sure कि whatever your assumption is, you have that noted down, because till the end of the question you'll want to use, जैसे यहाँ पे मुझे सही assumption use करना पड़ा, मतलब right assume किया तो यहाँ पे minus sign डालना पड़ा. तो make sure you either remember it till the end of the question or preferably you have that noted down. ये एक equation है, ये equation बताता है कि if I rearrange this, तो v by 2 is omega l by 2 minus v dash. So v dash हो जाएगा omega l by 2 minus v by 2. Okay, so I have v dash now. V dash is omega l by 2 minus v by 2. Right, इसको बस rearrange कर लिया. All good. The next equation, the second equation that we'll apply is now conservation of angular momentum. Same story, that hinge will not allow us to apply linear momentum conservation, but we'll conserve torque about the hinge. So angular momentum about the hinge. So about hinge, about the hinge, L of the particle, L of the particle initially plus L of the rod initially is L of the particle finally plus L of the rod finally. Okay. All right. While conserving angular momentum, take one direction to be positive. Linear momentum में तुम define करते थे ना, right is positive. वैसे ही यहाँ पे एक direction positive define कर लो as you're going to input things. So I am assuming this is positive. I'm assuming anti-clockwise is positive. ठीक है? This
everything will have the same direction here, right? Because
क्योंकि मैंने इसको ऐसा लिया, अगर मैं v डैश को अगर लेफ्ट की तरफ लेता तो पहले तो रिलेटिव वेलोसिटी में पॉजिटिव साइन आता और फिर जब मैं एंगुलर मोमेंटम इक्वेशन लिखूंगा आई विल हैव टू मेक श्योर इसका एंगुलर मोमेंटम इज रिटन एज अ नेगेटिव टर्म.
for the question it's like same direction, like same sign, like for this question.
For what I have assumed it towards the right, so that way it will have the same direction. Okay? All right. तो अभी इक्वेशन लिखते हैं, है ना? आई एम टेकिंग राइट एंटी क्लॉकवाइज इज पॉजिटिव. तो पहला रॉड पार्टिकल का एंगुलर मोमेंटम mv into r, डिस्टेंस इज l by 2, मास इज 2m, फॉर्मूला तो आ जाएगा 2m into velocity. Velocity is v into radius, distance, perpendicular distance is l by 2. Perfect. तो ये हो गया initial velocity for the angular momentum of the particle. Initial angular momentum of the rod is 0 because the rod is not moving. All good. Final angular momentum of the particle 2m, same story, 2m v dash l by 2. But अब I already know the value of v dash. So let's substitute v dash. Omega l minus v by 2. ठीक है, I'm substituting v dash. ठीक है, इसलिए पहले v dash निकाल दिया. Okay, omega l minus v by 2, l by 2. That is final angular momentum of the particle. Final angular momentum of the rod, I omega, ml square by 3 omega plus ml square by 3 omega. Okay, so now there's just one equation left and omega is the only unknown. Omega को right hand side पे रखेंगे, बाकी सबको left hand side पे लाएंगे. Let me cancel out whatever gets cancelled out. Okay, and then so I think क्या कटेगा, m कट जाएगा.
And we can cancel one L.
We can cancel one l. Great. ठीक है, and ये 2's कटेंगे. So this 2 and this 2, this 2 and this 2. See, so bring all the non-omega terms को इस side. तो ये यहाँ पे सिर्फ v रह गया और फिर वो क्या है, वो है अपना माइनस v by 2 सब कटने के बाद. उसको यहाँ पे लेके आ जाओगे तो प्लस v by 2 और ओमेगा को उधर रख दिया. तो ओमेगा एक टर्म है l ओमेगा by 3 और ये पहला वाला टर्म है l ओमेगा by 2. L omega by 2 plus L omega by 3. 5L omega by 6. Okay, so 3V by 2 is 5L omega by 6, which makes omega 9V by 5L. Was that your answer? 9V? That was very nice. Omega is 9V by 5L. Cool. Any doubts online? We'll stop here. Next class देखेंगे what if the rod was not hinged?
If rod is not hinged, then there wouldn't be like a reaction force by the hinge, right?
then could be so like conservation of angular linear momentum.
Yeah.
The axis is going to change. If it's not hinged, the axis of rotation will change.
For those online who can't hear what these guys are saying, so yeah, axis of rotation actually doesn't really matter. You can apply conservation of angular momentum about any axis as long as वहाँ पे torque 0 है. So जो तू बोल रहा था कि axis of rotation will change, वैसी बात नहीं है. When the rod is not hinged, there is going to be no hinge force. So there's no external force, there's no external torque. कोई भी axis के ऊपर external torque नहीं है. We'll see in the next class. You can choose any axis you want and conserve angular momentum about it. ठीक है, यहाँ पे सिर्फ hinge ले सकते थे, वहाँ पे कोई भी axis लेके angular momentum conserve कर सकते हैं. And as this guy was saying, you can conserve linear momentum as well in that case.
So that is going to be comparatively easier.
That's going to be more difficult. यहाँ पे 2 ही equation था, वहाँ पे 3 equation होगा. हाँ, क्या बोल रहा है?
They will give us more variables.
हाँ, so that will be more difficult because that will have more variables. यहाँ पे क्या है ना, यहाँ पे rod hinge था, तो rod का omega is all you need to know the motion of the rod.
So if the rod is unhinged, it will have translational motion also, right?
Perfect. So if the rod is unhinged, just omega is not enough to describe how the rod is moving. You need VCM as well. तो वहाँ पे VCM and omega दो मतलब एक extra unknown आ जाता है. So that makes it
थोड़ा rolling.
थोड़ा longer. And there'll be translation and rotation as well. Yes, in that sense, yes. There'll be one extra equation, one extra unknown. We'll see that in the next class, guys. Please catch up on your homework. I'll put some more in the group. Okay. See you. Bye bye. You have any homework doubts?
Actually had some.
You can put सकते हैं.
Yeah, mark the question.
Those who, yeah.
So question number
20
5.
booklet का 25. Okay. If you guys have not done this, no, and if you want to leave, you can leave. तुमने नहीं किया, and if you want to leave, you can leave. Just saying. A 5-meter long pole of 3 kg mass is placed against a smooth vertical wall as shown in the figure. In the equilibrium condition, that the pole makes an angle of 37 degrees with the horizontal frictional force between the pole and the horizontal surfaces. ठीक है, हाँ.
So I applied in my method. I applied NLN, and then after that, it's rotational equilibrium as well. So
Okay. तो तेरा क्या आंसर मैच नहीं हो रहा है, ऐसा कुछ है?
Yes.
Okay.
Sir, आप doubt lecture लोगे क्या for these homework?
हाँ, अरे सो भाई तेरे को ना जब भी मेरा इधर डाउट सेशन होता है, जब भी लेक्चर होता है उसके पहले डाउट सेशन होता है, लाइक आज भी था. सो जस्ट कम अ लिटिल अर्ली and get your doubts cleared.
Yeah, because the same doubts session रहेगा.
हाँ, तो उसके हिसाब से आ जाओ. And you can ask me, you can ask other teachers as well. किसी को भी पूछ सकते हैं. If you want to ask me, it will be on the same day as my lecture. ठीक है? तो क्लास में मतलब करने से अच्छा आउटसाइड क्लास करेंगे तो we can cover more. हाँ, जिस एक बार मुझे वैल्यूज बताए ना, यहाँ पे म्यू है.
Mu is not equal to this.
हाँ, और यहाँ पे कुछ लेंथ रॉड वगैरह क्या है?
Rod 5 meter.
5 meters लेंथ है इसका.
And for the wall, mu is 0.
हाँ, and what do you have to find?
Force of friction.
यहाँ पे है ना, force of friction. Okay, तो
So gravity will act at center of mass.
and this is not moving, right?
Yeah.
Okay.
So it's rotational equilibrium and linear.
हाँ, तो जैसा हाँ, तो quickly like the linear one will tell me. देख इसमें forces सिर्फ एक फ्रिक्शन, एक अपना mg होगा, एक यहाँ पे नॉर्मल होगा, ठीक है, फिर यहाँ पे एक नॉर्मल होगा n dash not important, और ये एक फ्रिक्शन होगा,
So and that would be equal to friction.
n dash will be equal to f, ठीक है, but
And mass is given as 3 kg.
mass is given as 3. So basically the normal is mg. Okay, the normal is going to be 30 Newton. Okay.
So
So-
after that we have a normal, we have to conserve and
हाँ.
the top should be.
किसके अबाउट किया तूने?
It doesn't matter because it's about any point that will be.
हाँ, that is true. Torque is, if torque is 0, you can apply it about any point. That's true. तूने but किस point के about लिया है equation लिखते वक्त?
So are you gonna give homework today?
I'll post in the group, ठीक है? But I would say तूने अब तक किया नहीं है ना? Just do last week's homework first. That's on the group,
Yeah, so I did it about the center of mass.
and I'll put fresh as well.
I did it about center of mass.
हाँ, so if you did about the center of mass, note कि n dash का भी torque आएगा.
So I've equated it to friction.
तो 3 torque आएगा.
Okay, so we could take another point where, okay, we could take it at that point. So and then f cutoff would be 0.
हाँ, you could take it up at that point. And that would be like the best choice. ठीक है? तो उसके about अगर torque लिखेंगे तो n dash का torque, which is going to be n dash L sin 37, right? Is equal to mg का torque, which is going to be mg L cos 37. Right?
mg L by 2 cos.
I'm so sorry, L by 2, L by 2 cos 37. And n dash is f. So f becomes mg by 2, L काट दिया, cot 37, which is 3 by 4 by 2 mg by 3 आ रहा है.
Okay. Okay, my method was correct.
हाँ, I think तूने just check, यहाँ पे गड़बड़ हुआ होगा. You may have not taken all 3.
Okay.
वो wall का या कोई किसी एक का
But the
mistake.
method was correct.
Hmm.
And then question number 36.
You guys have the homework ना पुराना वाला group पे. हाँ,
ये कौन सा क्वेश्चन है सर?
ये 15 था.
Exercise 1, right?
हाँ, exercise 1. तो कौन सा पूछ रहा है?
36.
36. Uniform rod mass m and length L hinged at its end is released from rest when it is in the horizontal position. The normal reaction at the hinge when the rod becomes vertical. Okay. So what did you do this question, man? Yeah, you didn't know what to do.
I use conservation of mechanical energy.
Huh. Perfect. So when the rod is vertical, they want the hinge reaction when the rod is vertical. So when the rod is vertical, you are going to have an mg acting on the rod. Okay?
Yeah.
And if you observe the center of mass ka motion, center of mass तो circular motion कर रहा होगा, right?
Yeah.
Circular motion कर रहा होगा, velocity vcm. तो circular motion करने के कारण एक v square by r acceleration होगा center के तरफ, right?
Okay, I missed that one.
अच्छा, you missed that one.
Yeah.
No, but you apply no conservation of.
Yeah, but like I got my forces, everything.
Achha. Should I continue? Or
The
you?
normal wouldn't be mg.
No, because the center of mass is accelerating
Hi, sir.
by. तो center of mass का एक vertical motion हो गया, ठीक है? and
दोनों का component है।
एक से ना, हाँ सेंटर मास का एक ये सर्कुलर मोशन कर रहा है ना, सर्कुलर मोशन करने के कारण it will have a radial acceleration and it may have a centripetal acceleration as well, which we can actually prove in this case is zero because torque is zero about the axis, but you'll have to be aware कि ये दो हो सकता है. And then when you say, when है ना, जब तुम बोल रहे हो कि यार hinge reaction is mg, तो so maybe I'll just explain this. तो देख
Could be wrong.
देख ठीक है, तो यहाँ पे first thing is I would say कि I'll apply torque about the hinge. When I apply torque about the hinge, ठीक है, I'll get zero. क्यों? देख ध्यान से देख, फोर्स तो तीन ही है, mg और जो भी hinge के कारण होगा उसके दो components. तो torque about the hinge is zero, which proves alpha is zero.
Yeah, because
I alpha. ठीक है. Now once alpha is zero, that proves कि ये hinge का अगर मैं hy और hx लिख रहा होता, hx is zero because है ना, there is no horizontal force, no horizontal acceleration, so no horizontal force. ठीक है. हाँ
HY 0 क्यों नहीं हो सकता?
अरे अभी तो अब लिखा ही नहीं है वाट का इक्वेशन,
अच्छा,
अभी वहां का इक्वेशन ये क्यों है वो दिख रहा है ना, r अल्फा इज जीरो, एक्सेलरेशन नहीं है हॉरिजॉन्टल डायरेक्शन में, ठीक है, जिसके कारण ये ऐसा हो रहा है.
so it's at rest vertically.
अरे एक सेकंड, who is at rest vertically? नहीं, कोई, nobody is at rest. This rod is released from this position, center of mass ऐसा circular motion कर रहा है. सर्कुलर मोशन करने के कारण हम उसका एक्सेलरेशन को एक रेडियल और टैंजेंशियल एक्सेलरेशन के फॉर्म में लिख रहे हैं. टैंजेंशियल एक्सेलरेशन जीरो है, अल्फा जीरो है, टॉर्क के कारण उससे प्रूव हो गया. हॉरिजॉन्टल फोर्स इज आल्सो जीरो. ठीक है. अब वर्टिकल इक्वेशन लिखोगे तो अपवर्ड डायरेक्शन में F इक्वल टू न्यूटन सेकंड लॉ, अपवर्ड डायरेक्शन में फोर्स Hy माइनस mg इज मास into upward acceleration VCM square by R. Okay? So I mean, first figure this out. Just because something is rotating does not mean you directly start by conservation of mechanical energy. Now the question was hinge reaction. So like first figure out, do you know what the hinge reaction is? Then when you see that term, you, acha, okay, I need to apply mechanical energy
Okay,
conservation.
this side directly took HY equal to 1.
हाँ. So then, so imagine like what I'm trying to say is, imagine this is a question in the exam. So then you wasted time applying energy conservation and then got a wrong answer.
Yeah.
Even if you're getting it wrong, it's better you start with what they've asked and get it wrong. At least you don't see a need to apply energy conservation and you don't waste time in it.
So
समझ रहा है ना क्या बोल रहा हूँ?
VCM square by R का डायरेक्शन क्या होगा?
मैंने F equal to ma लगाया. Upward force is mass into upward acceleration. VCM square by R upward है ना, सेंटर की तरफ, centripetal acceleration है.
And we get VCM by mechanical energy.
हाँ वो भी लिखो ये वहाँ.
What's the name of this topic?
Which one?
The question is based out of which topic?
So this is actually based on work energy theorem, and this is Newton's second law.
Yeah. And question number 41.
Yeah, you can read. The uniform cylinder mass m can rotate freely about its own axis, which is horizontal. A particular mass m0 hangs from the end of a light string. Moved around the cylinder, does not slip over it. When the system is allowed to move, the acceleration of the descending mass. सिलेंडर है, मास m है, m0 है. ओके, सिलेंडर का रेडियस ऐसा नहीं दिया है, मतलब मज्यूम करते हैं. Welcome. Huh? I'll solve it quickly. So, let's say यहाँ पे tension is T.
Yeah.
इसका weight is m naught g. ठीक है? And इसका acceleration downward is, let's say, a. Okay. All right. Which makes this guy's alpha. If you can see, this is at rest. So a is r alpha. है ना? ठीक है? तो इसका equation बताएगा m naught g minus t is m naught a. Right?
Yeah.
फिर
And
हाँ.
T into I is equal to I alpha.
हाँ. So t into r, I is going to be mr square by 2 into alpha, which is a by r. है? So ये सब r देगा, सब r कट जाएगा. So t is ma by 2. T is ma by 2.
Okay, I got it. I'm just trying to figure out whether
Hmm.
yeah. Okay.
Hmm. That's it.